Good morning, distinguished guests, speakers, ladies and gentlemen. It's a great pleasure for me and an honor to be here with you at our international workshop on unification in physics and philosophy at the House of Science and Letters here in Helsinki. It's my pleasure to welcome you all warmly. Our program is highly interesting, excellent, even brave, although first and foremost important for viewing and examining open questions and problems, as well as different possibilities in science today. When our focus is only on details of isolated topics, there are limited possibilities to develop unified views of interrelated domains in physics and philosophy. The ambitious aim is to get a general view of the situation and understand the history behind the present state. It's quite demanding or a difficult task. The attempts to address interrelations between physics and philosophy has been rare. I'm not a physicist or a philosopher, but an historian interested in the history of the mind and history of knowledge, and the long chain of thoughts and activities that are the base of human knowledge. In most fields of research, there is today two parallel trends. One toward multidisciplinary, interdisciplinary, cross-disciplinary, approaching a broader perspective, and another at the same time leading to fragmentation and focus on limited questions. Views on matters of unity and unification makes, however, a difference in many ways. They can give methodological guidance and even justification for hypotheses, or can help us to choose what sort of questions to pursue and what target areas to explore. The questions to be discussed here today include, but are not restricted to, the following. What are the central problems in physics and scientifically oriented philosophy? Can we identify postulates of provisional, scientifically and philosophically sound unified ontology? How do specific provisional postulates unify domains of inquiry that are currently separate, and how do they resolve their central problems? What are the criteria by which one theory is to be preferred over another? How did the historical development result in the current situation in physics and philosophy? Finally, it's my pleasure to present the excellent program committee of this workshop. Members of the program committee are Avril Styrman, Tuomo Suntola, Kari Kosonen, Tapio Ala-Nissilä, Heikki Sipilä, Juha Salmela, and me also. Now I think we are ready to start with our program of today. Chair for the morning session is Heikki Koivo, Professor Emeritus from the Aalto University. I wish you all an inspiring and interesting day here at the House of Science and Letters.
Good morning, everybody. So I'm Heikki Koivo, and I'm very happy that Avril has asked me to chair this morning session. So the first speaker is Avril Styrman, and he is the chair of the Finnish Society of Natural Philosophy, as you have seen. So, Avril, please.
Thank you. So, ladies and gentlemen, thank you all for coming. The topic of the introductory speech is unification, evaluation, and development of theories. So this speech is intended as an introduction for all the other more specific speeches. And the theme picture here, if it's still unclear for anybody It means that we have several different theories that use different postulates in explaining some phenomena. And then they are replaced by a single theory that explains all that the previous theories explain, but in a unified manner. We'll go through structure of theories, evaluation and development of theories, and then apply these to assessing the overall state of contemporary physics. First, structure of theories. So, is formed. Perception yields verified commitments or beliefs in the existence of particles, planets, or any objects and their movements. Then metaphysical commitments function as the basis of explaining the verified commitments. But metaphysics is itself unverified. That's one definition of metaphysics. It's a hypothesis that's unverified. So we have here a picture of ontology, consists of two parts. And ontology itself is what exists according to a theory. That's the ontology of a theory. So first, perceptions yield verified commitments or beliefs in the existence of things. And then metaphysics explains or function as a basis of explaining them. Of course, we have a great layer of mathematics then on top of the metaphysics. So everything posited by hypothesis is metaphysical. It has many names, like hypothesis of universal laws, unobservables, brute facts, primitives, axioms, unexplained explainers, hypothetical entities, and principles. All posited by hypothesis is metaphysical, and this is important later when we evaluate theories. One visualization of how a theory can be developed. First we have observations, they are the blue spots, and then we try to discover regularities, that's the blue line, and then postulate some law that governs the regularities. That's one simple way of representing how theories can be formed. Another example, theory about the solar system. First, for instance, how Newton deduced the universal law of gravitation, that F is G times N1 and M2 divided by R2. So first was the idea that the sun is in the center, and he had the regularities, the orbits of the planets that are exactified by mathematics. That's a formula on top left. And then he deduced that this is the law of gravitation that governs the regularities. One simple expression of how theories can be built. And then to evaluation. So we evaluate competing theories, then we assess the fitness of their predictions and explanations about the same phenomena. And when I talk about same phenomena, I can say like it's empirical data, perceptions, or verified commitments. So if we evaluate two theories, we have to have first know that what's their function. So if they are competing theories, they have the same function. So they try to explain and predict the same data. For instance, two competing theories of the solar system, two competing theories about the cosmological scale, or whatever specific phenomenon. So it's quite commonsensical that of two theories that predict and explain the same phenomena, the most virtuous is the best. But the question becomes, what are the virtues and how can they be measured? So what are the virtues of scientific theories? The study of virtues itself is a complicated area. I'll simplify this, concentrate on three main virtues. It's called evidential, accuracy of predictions, and depth of explanations. Then unifying power as the ratio of evidentiality and simplicity. And third, diachronic virtuousness, or the development of unifying power over time. So these are all tightly interconnected. Start with the primary virtue of evidentiality. It's called evidentiality because it can be measured by comparing a theory to empirical evidence. That's again accuracy of predictions and causal depth of explanations. Here Carl Hempel characterizes the difference of predictions and explanations. So while in the case of explanation, the final event is known to have happened, in the case of prediction, the final event is typically not yet taken place, but we have to predict it. And here predictions are like the final, the most wanted end result of science. Okay, again, accuracy of predictions, depth of explanations. So, if we talk about accuracy of predictions, it's first of all, it's easy to measure, because if we make an assessment that some planet will be tomorrow or within 1 year at this specific spot there, there's no enigma in measuring it. We can measure it. If it is there, the measurement, the prediction is correct. It's easy to assess accuracy. So that's one reason why it is the most important virtue. And it's also the most urgently needed. Whenever there is a dire need, it's more important to know how nature behaves and why. And thus, predictions are more important in this sense than explanations. And third, other virtues are subjugated to accuracy of predictions. It appears here too. So the other second evidential virtue is the causal depth of explanations. Again, accuracy in which an explanation characterizes phenomena. And second, the variability of circumstances where an explanation remains valid. And the final test for explanations is their prolificity of accurate predictions. So if an explanation provides, in the long run, it provides accurate predictions, then it's the final test for a scientific explanation. And we can see that 1 and 2 feed 3. So if we have an accurate description of some phenomena, then it's easy to form, or possible to form, a prediction based on the description. But evidentiality is not enough in theory evaluation, because we cannot select between two equally evidential theories based on their evidentiality only. So there are two theories that are exactly as accurate and have exactly as deep explanations, so we can't choose how to choose between them. So the solution is to evaluate other virtues. And here I selected as the second most important virtue, unifying power. It's called Unifying Power, the principle of economy, parsimony, Occam's razor. They are very closely related, almost the same thing. All state that of equally evidential theories, the simplest is the best. So we have evidentiality divided by simplicity. So first, we select the most accurate theory, or most evidential theory. And if there are two theories that are equally evidential, then we go on to evaluating their simplicities. And evidentiality is abbreviated as E and simplicity as M, denotes M as metaphysical simplicity. We have two main types of simplicity. It's metaphysical and syntactical. So metaphysically simpler theory commits to a smaller number of hypothetical entities or laws or principles. So it just has a smaller metaphysical weight. And syntactically or mathematically simpler theory has a simpler formulation. But we use here simplicity as a fusion of both, but mainly metaphysical simplicity, but also mathematical or syntactical simplicity. And they are at least partially dependent. Here we have many, many historical quotations that conform to this ratio of evidentiality and simplicity. For instance, Thomas Aquinas says, if a thing can done be adequately by means of one, it is superfluous to do it by means of several. So if we get the sufficient evidentiality by means of one postulate, then it's superfluous to do it by means of several postulates. And exactly the same notion by William of Ockham and Isaac Newton. But perhaps the first formulation of this unifying power as a ratio, specifically as a ratio, is by Eino Kaila, who's in fact Finnish. So he says the smaller the number of its logically independent basic statements, that's simplicity, in comparison to the number of different kinds of facts that can be derived from it, the greater is the relative simplicity of the theory. So relative simplicity here can be interpreted to be exactly the same as unifying power. And Philip Kitcher's unification model, the basic idea of unification or scientific explaining in the unification model is about unifying disparate phenomena under a small number of basic principles or patterns that resembles the fraction or ratio of evidentiality and simplicity. Then, the development of theories as the development of unifying power. Again, the same ratio. So we observe unificatory versus disunificatory development that is roughly analogous with the positive versus negative development or success versus regress. So unification, that's success, disunification, that's regress. So I use this graph. On the horizontal axis, time and data grow. So time goes forward, the amount of empirical data or phenomena to be explained grows. So we have more and more phenomena to be explained by the theories. And it's supposed that all theories that we analyze, they succeed in explaining, predicting the data. So that's this curve, E, evidentiality. So we suppose as time goes forward and the amount of data increases, all the theories, they actually succeed in explaining them. So we ask, what is the cost of explaining? And we measure the cost by the amount of metaphysics that is needed in explaining them. So here is the dotted line, that's amount of metaphysics. And in this picture, it stays constant. Here it increases slightly. Here, metaphysics is equal to evidentiality. And here, even more metaphysics is needed than evidentiality. Okay. Then the blue dashed dotted line is unifying power. And we see that if the amount of metaphysics grows faster than the amount of phenomena to be explained, that have been explained, then their fraction or unifying power, it decreases. Of course, if M is higher than E, then their fraction gets lower. Now, if they're identical, then their fraction is constant. And if metaphysics increases only little, then their fraction is as you see. And if metaphysics stays constant, then unifying power is identical to evidentiality. And we directly jump from here into unificatory development. So, if our theory manages to explain all the data, all new data by its basic structure, then that's a sign of success and rising unifying power. Good examples are Newtonian mechanics, studied mathematical physics, was highly successful for the first 100 years and more, explained all new data. Another example, the famous periodic table of elements that managed to explain our data, all elements, and managed to predict new elements. Then in contrast, disunificatory development. That's about parametrization. When a theory fails to give correct predictions of new data, it can be saved from falsification by accommodating the data by parameters, additional parameters. When data is accommodated by the aid of additional metaphysics, the reality is, so to speak, complemented by hypothetical entities in order to save the theory from falsification. And here we have a quote from Karl Popper, one of the most famous philosophers of science, 20th century. He says that no conclusive disproof of a theory can ever be produced, and it's always possible to say that the experimental results are not reliable. Basically, all problems will disappear with the advance of our understanding. But however, we can measure these problems, the degree of these problems, by measuring the amount of metaphysics. So one cannot hide the ad hoc parameters that are these additional repair parameters. Of course, there's sometimes debate on what is metaphysics and what is empirical fact. But if we apply the definition that it is supposed but not perceived, then it's metaphysics. And here we see that metaphysics rises faster than evidentiality, so more hypotheses than new kinds of data, unifying power decreases, or if there's like new hypotheses for each new kind of data, then unifying power stays constant. And that's also negative. So all development where unifying power does not increase is negative, supposed that data grows. A good example is standard cosmology. If you look at the situation before the accurate measurements of Ia supernova, so we had the standard model prediction here. But when the supernova measurements came out, people saw that the curve misses the target. So the curve is below the target. So those crosses there, they are the measurements, and then the curve predicts them. And then dark energy was added to the model, and the curve was fit in place. So we have a good reason to believe that dark energy is in fact this kind of a repair parameter that was added to save the theory. Of course, it's not a consensual conclusion. Many physicists think that, okay, dark energy is an empirical fact, but not all agree. Many think that it's just a parameter, not real, just invented to save the theory. The scientific community has strong faith in standard theories. So here's a picture of Nobel Prize for the acceleration of discovery of the accelerating expansion of universe. What happened was, as we saw, that predictions did not match perceptions, dark energy was added, and then it was deduced that the universe is accelerating because dark energy makes it accelerate. And then the Nobels for the deduction and for the measurements. Okay, now we apply what was said before to assessing the present state of physics. So this is, of course, very great simplification, just to create a contrast. At the time when Newton discovered made the Principia Mathematica, so there was great success, unificatory development. But in the 20th century, even before that, things started to change. Not so positive anymore. So what happened in short, was that Newtonian mechanics was, could be also said it was replaced, but it can be also said in a simplified way it was modified and complemented, also modified in a very substantial way by theory of relativity, special and general, and then general relativity-based cosmology. And we do have parameterization and problems there a great deal. And then quantum mechanics was created, works like clockwork, but no consensual ontological interpretation. And also the ontological interpretation of theory of relativity is not finished. So the basic picture with relativity and quantum mechanics is mathematics works very well, but the worldview behind it is like it's completely messed up. Nobody knows what it is. There's been 100 years of speculation. And as well known, theory of relativity and quantum mechanics start from different principles. So we have disunified worldview, scientific worldview. And also a standard model of particle physics, a lot of parameterization and problems. So the other speakers of the morning session open up these issues in a lot more detail. There's just an overall notion of the case. We get back to this picture. So when the standard theories, or standard theory of theories work, then normal science suffices. If there's no problem, of course, then there's no problem. Everything works. But if not, there are great problems that we can measure by seeing that the amount of metaphysics grows. The normal science is not enough. According to Thomas Kuhn, this kind of development seen on the right, it leads to a paradigm shift. That the failure of existing rules is a prelude to the search for new ones. That's Kuhn's influential book. So we see that normal science is not enough when we need new theories. So the main challenge is to invent better theories. And here's a picture again, that better, more unified theories. And another challenge, sorry for the index numbers, is dogmatism or stagnation in science. So you can see the circle of stagnation kind of prevents the optimal progress rate. But we know that standard physics is highly parameterized and disunified. So normal science is not enough and new theories are needed. But the scientific community effectively repels new theories because they contradict the standard theories. So there is this stagnation phenomenon is present in science. And standard theories are taught to students without criticism, and the tradition goes on. So again, a quote from Karl Popper. He says that normal science exists, of course, always exists, and it's very important. But at times of crisis, it's not the only thing that we need. It's the activity of non-revolutionary, not too critical professional. So Kuhn says he is sorry for the normal scientists. No, we perhaps should not be sorry for normal scientists, but it's a problem if it goes too far. If we need change and then somebody doesn't want change because somebody wants to keep on the normal science, then that's a problem. To sum up, we need new theories that are more unified than the standard theories. We must objectively evaluate new suggestions against standard theories. And to reach the optimal progress rate of science, we should also accept better theories, even when they are different from standard theories. Thank you.
Thank you, Avril. Then we have time for questions.
we want to unify the fundamental back from both theories. But we need not to unify them as they are.
Oh, so you mean that we do not need to
quantize gravity because it's ridiculous to try it.
Okay, so you mean that okay, we do not need to unify theory of relativity and quantum mechanics, but we need just a unified theory that explains the phenomena. Yeah, okay, I agree perfectly. And but while I think that while quantum mechanics, there's no great needs for change. There is a great need to reject theory of relativity. That's a real problem, I think. So we have to have a theory of gravitation that's unified with mathematics of quantum mechanics.
Wait for Tuomo's presentation. Please.
Yeah, thank you. Yeah, one question or opinion. I think if there is a possibility or if we can find a unified theory, of course it's better to have a unified theory. It explains the whole thing. Better than try to, let's say, go behind the deviations. Okay, this is a deviation and then we have this explanation. Everything it's better to find a unified. If we can find a unified theory, then it's much better. And I think that nature always works in the very simple way. And in nature, I mean that if we can find the basic theory, which goes according to nature, it's much better. Thank you.
Okay, I absolutely agree.
Thank you. I enjoyed your curves with the increasing amount of evidence and then the increasing or stable amount of metaphysics and the ratio between those. So I agree that with our capabilities in instrumentation and measurements, we get so much more and more data all the way. But perhaps it is not so, our human mind is so limited of being able to find so simple mathematical principles in order to be able to catch in this range. So could it be just that this is vain thing to find the unified theory? Perhaps the world is just so complex that there is no way of finding a unified theory with this increasing amount of complexity that we find there, deeper and deeper level, like macroscopic and macroscopic level of the cosmos.
Thank you for the question. That's of course, if you decide, then that's it. So we can decide, okay, somebody wants unified theory, somebody doesn't. So that's it. But if you look at the history, like in the 18th century, like unification or unifying power was a commonly accepted virtue by like many great scientists, all committed to that. But then in the 20th century, things have changed. So when the contemporary basic science isn't unified anymore, so people have started thinking that, okay, maybe unifying power or unification is not the goal after all. So it seems that the valuation or the appreciation of different virtues, scientific virtues, they change at least partially along with the theories. So if we have unified science, people appreciate unification. A disunified science, people don't appreciate unification so much. But then again, I just can't accept that we wouldn't want unified science. It's so like, it seems so evident that it's so much better and easier if everybody would agree and there's so much synergy and understanding, because now there's no real understanding. Like imagine, compared to Newton's times, everybody thought they had a clear picture of how nature works. But now there's no such thing. I think it's like very, very generic desire for humans to understand. So unification was hand in hand by understanding. That's why we need it.
Share that gentleman's concern about the complexity of data and share your yearning for unified theory as well. I was wondering whether in the 20th century, the data you're collecting has reached such a level of complexity that you can't decouple the observational data you collect. You get to the point where you're down the same rabbit hole. You know, once you use that data, you've basically bought into the theories that sort of kind of go in step with the observational data, and you try to come up with a theory on that. By virtue of that, you've assumed a lot of the data that is dependent upon a lot of the previous theories, and they've built in such a way that the only data you can get these days are so complicated that not every person can get their hands on data. Whereas in the 17th century, you can sit down under a tree, look at the sky, and come up with various pieces of data. Nowadays, you need levels of electron microscope, accelerators, and things like that. And so by the time you get there, you've bought into the whole package. And it's hard to come up with a new theory and decouple yourself. So what do you say about that? To couple the observation data with a theoretical?
By the way, give the microphone to people, please. That, there. So you're talking about that, what is empirical data, even that is theory dependent, at least partially. Yes. We know that it's so complicated, everything's so complicated. Even the question of what is empirical data is debated. And then you have to understand, even the theories a little bit to know what they are, what's the data that they are about. So there's no problem for me to accepting that that's a real challenge. Like it's so complicated and so diverse, and so we should understand even the data before we can even understand the theories. Are you saying that?
Yeah, you can't really create a whole new data set from scratch these days. You know, you basically have to go with open data out there. And that entails some degree of acceptance of existing theories, by which point you can't really come out with a completely new and different theory as you're proposing. Do you agree?
Well, I'm not proposing that we need completely new different theories, but what I'm proposing that at least there are basic assumptions. For instance, we take theory of relativity, its postulates. Then I think that those must be changed in order to reach an understandable worldview. So we cannot let the time vary locally if we want to understand reality, for instance. But the mathematics of the theory, whatever it will be, will certainly look a little bit similar. So.
Thank you. Well, you said, referred to the idea that the simplicity, the most simplest, is the best one. On what basis? How come? Is in that estimation, will then the most simple one be the goal or the means, or both of them?
So the eventual justification of simplicity is to understand that it's self-evident. So, and because we first take two theories that are equally accurate and evidential, so what other criteria can we use, in fact, than simplicity? Of course, there's a lot of different criteria that some, especially in the 20th century, scientists have considered that beauty is maybe the most important, even the most important theory. But then it's even at the face of it, it sounds like it's not objective. Because we know that from historical studies that scientists think that the familiar theories are beautiful. So beauty is not really a reliable criterion. And then there's also coherence. Of course, we like internal consistency. That's good. And then consistency with other theories. But hey, consider the Earth-centered theory and compare it to Copernicus' theory. So it was inconsistent with the body, the basic theory of that time. But it turned out that the sun-centered theory is better. So even consistency with standard theories is not reliable or good criterion at the times when we need change. So then we arrived at simplicity as the main criterion. So you asked why simplicity? So, of course, first, that it's easier to understand if it's simpler, typically. And then imagine that you have theory that has like 5 different postulates, ad hoc parameters. That's like, you cannot understand really reality if you have to parameterize it. So, again, simplicity goes together with understanding. If we want to understand, then simplicity is good criteria. And easier to use, simpler is easier to use. It's methodologically like more virtuous. So simpler to test, easier to test, simpler hypotheses. That's one very famous case. So I can only appeal to these kinds of principles that's easier for people to handle simpler theories.
Okay, this is what Avril has been asking for, questions and discussion and so on, but now I think we better move on. Last big question, I hope.
Okay, I agree this simplicity. For example, Sabine Hossenfelder speaks for no beauty or prefer ugly theories, so that when we have some parameter, they hope to add more parameters to go forward. I think this is madness. Of course, we need simplicity and beauty. And for example, virtual photons, you mentioned dark energy. They are ugly. They are no good, I think. We need focus on fundamental things, just like interactions. Just like we are mammals, we see 3D, but the nature is no 3D or 4D. There are no dimensions. There are only interactions, and so we must concentrate on the fundamental things and simplicity.
Ever since the unification of electric and magnetic fields by James Maxwell, the unification of gravitational and electromagnetic fields has become the dream of physics community since early 20th century. The early attempts of unification by Will, Eddington, Caruso, and Einstein all failed. Unification along the approach of quantum field theory is called the theory of everything, which requires an energy in the order of 10 to 19th GeV, known as the Planck energy, and also requires an accelerator larger than solar system. It is absolutely impossible. The reason for the failure is that general relativity is incompatible with quantum mechanics because it is not renormalizable. Recently, I have developed a theory of unification of gravitational and electromagnetic forces without resorting to general relativity and quantum field theory, and the theory was published in the book. The theory predicts that the gravitational wave propagates with the same speed of light. And in the theory, we have a new discovery. I christen it as the Wang's law, which says that the total linear momentum of the gravitational field propagated into space is conserved. The failure of the mainstream to unify the gravitational force reveals many fundamental problems of the standard doctrine of the theoretical physics. The first problem is that the approach of the theoretical physics of 20th century to the understanding of microscopic world is wrong. Instead of studying the structure of the radioactive nuclides, the theorists of the 20th century were engaged in the study of the structure of the nucleons, including the proton. The right approach to the microscopic world is the study of the over 2,000 nuclear isotopes, which will show some regularities, even periodicity, that would be suggestive of the nuclear structure. So a systematic experimental study of the nuclear isotopes will not only lead us to the understanding of the nuclear structure, but also highly possible to the discovery of some new nuclear fuels and realize controlled thermonuclear fusion. Whichever country who first takes this new approach would be the first to jump out of the abyss and emerge as the world leader in science and technology. The second problem with the microscopic physics is that it is impossible to understand the microscopic world through collisional experiments. According to quantum theory, the differential cross-section, d sigma d omega, is equal to the integration of the interaction potential V sandwiched in the wave function psi and its complex conjugate integrated over the whole space. Our job, the job of theorists, is to determine the integrand, that is V and the phi, including the wave function and the interaction potential, based on the value of the definite integration on the left side. But this is an impossible job. For example, the mass of a solid can be calculated by integration of the mass density and the shape of the solid. But the opposite is not possible. That is, if you give the integrand, you can find the value of definite integration. However, given the value of definite integration n, it's impossible to find the form of the integrand. To determine the interaction Lagrangian and the wave function based on cross-sectional measurement is fundamentally speculative and highly impossible. To make the speculative job a little easier, some restrictions are imposed on the forms of the wave functions and the interaction potentials, or Lagrangians, in the name of symmetry and mathematical beauty. The early concept of the symmetry includes CPT conservation, that is charge parity and time reversal. The more general concept of symmetry means that the theory remains invariant under certain transformation. The most important symmetries are the Lorentz invariance and the gauge invariance. The standard model of the particle physics is built upon the gauge field theory. The gauge field is also known as the Yang-Mills gauge. Now, one of the problems is that the gauge field theory does not allow any particle to carry mass because it destroys the gauge symmetry. It was then hypothesized that there exists an omnipresent God particle or Higgs field that allows other particles to obtain masses through a mechanism called the symmetry breaking. So here we have a philosophical question. Is the nature fundamentally symmetrical or asymmetrical? If the nature is fundamentally symmetrical, why do all particles have to obtain masses through symmetry breaking? If the nature is fundamentally asymmetrical, why should the symmetry be imposed upon a theory in the first place? Logically, the action of obtaining mass should not take longer than the lifetime of the God particle. It is like the first push by God. Newton's first push does not need a term of God in his law of gravitation. But God particle has to coexist with the proton and electron all the time in the same Lagrangian of the Standard Model. Although there is a world difference between the lifetimes of God particle and the proton. Namely, the God particle, which has a lifetime of 10 to negative 22 seconds, and proton has a lifetime of 10 raised to positive 38 years, which is 25 orders of magnitude longer than the Big Bang universe. Now, these particles cannot coexist all the time. Another serious problem is that the elementary particles are no longer elementary. There are hundreds species of animals in the particle zoo or particle botanical garden. There is no control of the ever-expanding size of the zoo. If you support the superstring theory or supersymmetry, then the number of particles is going to be doubled. The reason for German and Zwick to propose the quark model was to reduce the number of species of the elementary particles. With the standard quark model, the number of elementary particles has reduced to 61, not including the various non-orthodox particles proposed by the so-called theory beyond the standard model. Even 61 is still too large for particles to be elementary. And that includes 36 quarks and antiquarks, 12 leptons and antileptons, 8 gluons, 3 vector bosons, and photon and graviton. The reason for the explosion of number of elementary particles was the identification of the resonances and excited states as particles based on Einstein's mass-energy equivalence. The resonances are actually the peaks in the plots of cross-sectional spectra, not really particles. I have shown in one of my publications that mass and energy are not the same thing. They are not the same physical quantities. Mass is a measure of the quantity of the matter. Energy is a measure of the quantity of the motion or state. For details, you are referred to this publication. The whole business of the particle physics in the last 70 years was the classification and categorization of the particle zoo, largely occupied by the resonances. If the resonances are not particles, the 70 years of particle physics would be a great joke. And there's a shift of paradigm, which the mainstream physicists are proud of, but that's where exactly the problem is. There's a dramatic shift of paradigm in the theoretical physics of 20th century. in fundamental postulations, methodology, in logic, in experimental evaluation and verification, and in the sense of mission in philosophy. But now there seems to be an experiment in LHC that shows some little peak at the right energy about 125 GeV. Ha! We found the God particle. It was rewarded the Nobel Prize immediately. If that's not confirming the existing theory, it would be considered faded again until another positive confirmative results. And you see, that's a shift of experimental verification from the classical attitude. Let me name a few shifts of paradigm. In classical, the classical space and time are mutually independent and independent on the velocity and the observer. The space and time are infinite. There's no time origin. There's no final point of time. It's infinite in both ways. The time is one directional. Namely, I cannot go back and become a schoolboy. In modern theoretical physics, space and time are mutually dependent and dependent on velocity and observer. The space and time may be finite. Time can go back to the past. Some of you probably have learned this grandfather paradox. You can go back to the past by riding on a time machine. You met a man raping a woman. So killed him and rescued a woman. But that man happened to be your grandfather. If he is killed, then the raping is not happening. Your father and yourself will not be existent. If you are not existent, you will not be riding back to the past on a time machine, and your grandfather would succeed, and you would exist. This is a well-known grandfather paradox. It reveals the absurdity of the time travel. In classical physics, mass and charge are fundamental quantities. Charge and mass of a particle are constants. Mass is a measure of quantity of the substance, inertia, and its gravitating strength. Energy is a measure of movement or state. Energy is essentially different quantity from mass. In theoretical physics of 20th century, mass of an object is dependent on velocity. But charge is invariant. It does not depend on velocity. All particles must obtain masses through God particle, but charge does not need to be obtained through such mechanism. In classical physics, the mass conservation law, the momentum conservation law, and the energy conservation law cannot be violated. Mass and energy cannot be created nor destroyed. Creationism is a direct antithesis to science. In theoretical physics of 20th century, however, the mass conservation law, the momentum conservation law, and the energy conservation law have all been violated. Creation and the annihilation of particles and antiparticles are stipulated in the standard procedure of quantum field theory, known as the second quantization. In quantum bubble theory, Stephen Hawking claimed that in a tiny volume of 1 cubic centimeter, which is smaller than your eye, there were 10 raised to 143 universes created per second, all connected to our universe through wormholes. We probably lost the sense of what is 10 raised to 143. I can tell you Google is 10 raised to 100. This is 43 orders of magnitude greater than a Google. This birth rate is much more dramatic and violent than a nuclear explosion. Now, a nuclear bomb can put the 10 raised to 23 molecules into the space in the mushroom. And this is much more violent than that. So you don't know how many universes have been created during the period since we started this section. Out of window, out of your eyes, you don't know the pain, you don't see it. But nonetheless, Stephen Hawking can calculate it with mathematics. Classical physics holds some logic inviolable. For example, a part of any object is always less, at most equal to, the whole thing. We call it logic. Causality is inviolable. In theoretical physics of 20th century, no logic is inviolable in the name of shift of paradigm. Violation of causality has become a favorite, fashionable, and fascinating idea for sci-fi movies. The mass of a particle can be less than the mass of the parts making up of the particle. For example, the massless photon, which has a zero mass, is assumed in the standard model to be a linear combination of massive particles of neutral B and W. And how heavy is W particle? It's 90 or 80 GeV. That is, it's about 100 times heavier than proton. You need that to be a part of a photon. So no logic is not inviolable. And there's a shift of scientific mission. What is classical mission of physics? Classical mission of physics is to promote the progress of human civilization, to provide the theoretical tools for scientists and engineers in their applications. Application of fundamental science is the ultimate test of a theory. But the mission of modern theoretical physics has shifted to finding a theory of everything, building a Babel tower and understanding God's mind. Theoretical physics has become an isolated, closed club, having nothing to do with any other branch of science, including nuclear physics, which was the hometown of particle physics. Many breakthroughs have been claimed over the last decades, but the rest of science remains unaffected and intact. And there's a shift of epistemology. Yeah, just tell me when to stop. 2 more minutes? Yeah. The classical physics believes that the nature can be learned through experimental investigation and logical reasoning and mathematical analysis. But theoretical physicists of 20th century believe that some laws of nature can only be studied by theorists on the scratch papers, such as the phenomena in other universes, if such universe exists at all, in the higher dimension, before the Big Bang or after the Big Crunch. Those are not understandable, but we theorists understand it anyway. They are smarter than the Wizard of Oz. The classical physics believes that science will advance indefinitely with deeper and deeper understanding of natural laws. But there will never be exhaust of the laws of nature. There is no final theory of everything. If a final theory of everything is found, then science is dead. The orthodox physicists of 20th century believe that they will find a theory of everything very soon. Maybe at the end of 20th century, according to Stephen Hawking, or a little later. But I can make a prediction here. It will never be found. If that's found,
I think it's about time.
okay. I'll just show the last slide. And some of, so the conclusion is emperors, all clothes are prettier and more effective in identifying the competent from those who are not. And I would like to present my book as a gift to the Society of History for Cecilia for Science and Learning.
Thank you very much. It's a pleasure. Very interesting speech. Thank you.
Our next speaker is Professor Unnikrishnan from Tata Institute of Fundamental Research, Mumbai, India. And the topic is a new gravitational paradigm for relativity, dynamics, and the philosophical basis.
Friends, thank you all for a warm welcome to Finland. I'll be talking to you on a new gravitational paradigm for relativity, dynamics, and their philosophical basis. And I want to focus on empirical evidence which all of you can relate to and understand. And then as we progress, it will be clear why these empirical evidences demand a renewal, reassessment of the existing theories. Physics is our body of knowledge on matter, motion, and interactions. And this knowledge can be built up only by adding our understanding or internalizing to what we sense or perceive, the empirical data. Then we add postulates and hypotheses to the empirical data. Thus we build up the physical theory, which consists of both observations and unobservables. There are many unobservables in physics. Due to this structure of physical theories, this necessary structure of physical theories, they are susceptible to changes. Even a single crucial observation and new insight can sometimes overthrow a full physical theory, which we have been holding sacred probably for a century or more. So, let me present this in a particular way. Suppose we are told and shown that a fundamental theory we all believe in for more than a century is in fact in gross error and shown evidence for that fact. What will be our reaction? This will be probably more jolting and realizing several hundred years ago that the Earth was not at the center of the planetary system. What I mean is, see, everyone in this hall would have gone through various turmoils of a sociological nature or a personal nature, financial nature, and so on. But it's very unlikely that any of us here today has gone through intellectual turmoil of the kind faced by Galileo or Copernicus or those people in the dawn of the century dealing with the difficulties in relativity and so on, or even quantum mechanics. So I am talking about intellectual turmoil of that scale, suppose you are shown empirical data which shows to you that the sacred theory, the theories we hold sacred for a century, they are in gross error. Suppose we are in a situation like that, what will be our reaction? How will we, are we willing to accept the new empirical data which will show that the theories are wrong? So what I want to present here is easily verifiable and understandable empirical data of measurements on time or electrodynamics and so on, and lead you through this new empirical evidence. So let me start with a very simple example. This is especially important for students here who are taught how clocks behave when they move in relativity. So we all know that clocks that move relatively ages more slowly, time dilation in special relativity. And special relativity has a very simple formula for time dilation. The clock which is moving, it has a time which is signified by the capital T. It depends on how much the clock moves through space, dx. So it is dt square minus dx square essentially. So all moving clocks should slow down according to our standard theory. So for example, if you have two clocks synchronized, one clock moves, comes back to the same clock, then you can compare these two clocks and you will see, you are supposed to see the clock that moved loses time, it ages more slowly. Okay, there is a formula which describes this phenomena. Of course, there is no reason why this happens. The reason is given as the clock moved, therefore it runs slowly. That's the only reason which is given. Now, let's take an actual example where two such clocks are synchronized, let's say in Bombay. And I move one clock a certain distance. And now at this stage, I cannot compare these two clocks because they are far away. To compare this clock, either I have to bring it back, or I can do one thing, I can move it along the same direction more, like that, keep moving, and finally the clock can come from the other side of the globe, and then I can compare this clock without retracing the path of this clock. So a clock has moved and come back to the old clock. And everybody who subscribe to the standard theory would say this clock should have time dilation. What is the actual fact? The clock which moved this way actually runs faster and not slower. This is evident in GPS every day. You may not be familiar with this result, but this is a fact. A clock which is transported westwards and continuously around the globe and brought back runs faster and not slower. This is the first evidence I wanted to present. So this formula is wrong. It is incorrect. It is proven as wrong every day in GPS-related clock comparisons. Now let's go to another example. This is a beginning of Einstein's 1905 paper. He says, it is known that Maxwell electrodynamics, as usually understood at the present time, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor depends only on the relative motion of the conductor and the magnet. And that is precisely why Einstein was looking for a theory in which relative velocities will appear. And the example which he was looking is the following. Take a magnet, put a conductor on top, on one of the poles, unipolar. Then you can move the conductor. then a current will flow in this conductor. Or you can move the magnet instead of the conductor. And again, a current will flow in the conductor. And these two phenomena are physically equivalent in terms of actual empirical observation. And if you move the whole thing together like this, for example, you move the conductor, you get a current. You move the magnet, you get a current. Both can be described in terms of the Lorentz force, B cross B forces. And when you move the whole thing together, where there is no relative velocity, you don't get any current. And this is the basis of electrodynamics of moving bodies in special theory of relativity. That's the reason for the title of that paper. However, Einstein was not fully aware of the entire empirical situation. You can also do the following. You take a circular disk magnet and move a conductor like this. Of course, another possibility is you can move the magnet instead of the conductor. Or you can move the whole thing together. There is no relative motion. These experiments were done by Faraday in 1832-1833 and followed up by Ampere. So, and this is described in his very charming Beckerian lectures, Experimental Researches in Electricity, second series. So when you move like this, there is a current in the conductor, exactly as when you move a conductor over a magnet, same thing. And you can describe this mathematically correctly. When you move the magnet, you may not be familiar with this result, there is no current. There is absolutely no current. It is not relative motion. This kind of experiments any laboratory can do, we do ourselves. Or you can move the whole thing together. There is no relative motion here. And this is where Faraday was really surprised. There is a current. This is a famous unipolar induction, which you don't even find in a textbook on electrodynamics these days. Okay? So, I'm just giving you different empirical observations already existing. This statement depends only on the relative motion of the conductor and the magnet in this paper is incorrect. He made that statement because he had only partial knowledge of the empirical evidence of the times. Now, when we go to the theory of relativity, it is described in empty space, what is called a Minkowski space. Absolutely empty space. And the absolutely empty space is homogeneous and isotropic. It looks isotropic and homogeneous anyway. Even when you move through empty space, it remains empty, it remains isotropic, remains homogeneous. And this is the reason for Lorentz transformation, because you start with empty space, homogeneous isotropic metric, Minkowski metric, and when you do Lorentz transformation, you get back the same metric. That's the logic of Lorentz transformation. However, what is the real world in which we live in? It is not empty. There is a lot of matter. For example, if you are in a moving frame, this is what we see, right? In a moving frame, we see a current of matter. Every moving frame has a current of matter, and space is anisotropic. Space might be homogeneous, but it's anisotropic. So, when you move through real universe, real space in which we live in, the space doesn't remain isotropic. It becomes anisotropic. And so I present this logical problem, which is very, very serious. All our fundamental theories, theory of relativity, theory of gravity, general relativity, theory of quantum mechanics, all these theories were completed well before we acquired any significant knowledge about the physical universe, its content, and its long-term evolution. We didn't know any cosmology by 1930. By 1930, we had completed all our fundamental theories. We follow the same fundamental theories 100 years after now. Those theories have not changed. But the new knowledge which came to us after 1930 is a new knowledge of cosmology. How much matter is there? What is the extent of our universe? All this is new knowledge. Imagine you make a theory of life, breathing, and so on, before somebody discovered the existence of oxygen. You will have probably a theory which works, but that theory will be factually incorrect because oxygen had not been discovered by the time you finish your theory. The discovery of oxygen comes later, which explains what is happening in terms of the chemical reaction and so on. Then you have to change your theory of breathing and life. If you don't change your old theory, which doesn't include oxygen, such a theory is bound to be incorrect. This is exactly what happens in the case of Avril. When I say exactly, analogously, the knowledge about the universe came later, much after you finish your theories. So therefore, your theory which doesn't include the matter and its gravity, your theory which claims that you live in an empty Minkowski space, is bound to be wrong, logically speaking. But logic is not enough. I have to give empirical evidence, because that is the decider of physics. So as I said, in particular, theories of relativity, dynamics, and all that were done before the universe, knowledge about the universe. In reality, space is not empty. It has matter and gravity, which is an important thing. It's not just matter. There is gravity everywhere at an average density, which we know about very precisely now. So all of physics and human activities are done in the enormous gravitational potential of the cosmic matter, whereas fundamental theories, as constructed, do not include these effects. Therefore, a major reconsideration, at least, is necessary, but nobody is doing that obvious reconsideration. So there is exactly one frame in which all the matter in the universe look essentially at rest. It's the same frame in which we see the cosmic microwave background isotropic and homogeneous. If you move in this universe, what you see is a moving galaxies, a current of matter, a current of charge of gravity, and you will also see the dipole anisotropy of the cosmic microwave background. You will not see an isotropic space. For people, especially students, I want to just indicate that it is a metric which changes into something. If it is Lorentz transformation, it remains, of course, invariant, Minkowski metric. But we know that space is anisotropic. It doesn't remain invariant. So Lorentz transformation must be inconsistent at some level. It cannot be the correct transformation. We live in what is called a Friedman-Robertson-Walker metric with space and matter. So why are we living in such logical poverty, blind to simple facts? Let's look at the actual metric. So, as I said, there is clear empirical evidence against the Lorentz transformation, at least the logical integrity of Lorentz transformation as a correct transformation. But we know that phenomena like time dilation are verified phenomena. Without Lorentz transformation, how can you get time dilation? You can ask me that question. And I am bound to answer this correctly. So I will show you what I call a simple and profound miracle. Because there is no other, since people have not noticed it before, there is no other way to describe it. So this is a metric which is standard Robertson-Walker metric. Since expansion of the universe is very, very slow, we can consider it approximately like a Minkowski metric. But when we move, I said there is anisotropy. So I do a Galilean transformation. It is not Lorentz transformation. Galilean transformation, x prime is equal to x minus vt and t prime is equal to t. What do I get? I get a new metric. This is what you get. Anybody can verify that. You see the miracle. I have done a Galilean transformation and I see the famous time dilation term 1 minus v square by c square coming out of a Galilean transformation. It has nothing to do with Lorentz transformation. And there is another term v dx by dx dt, which is an anisotropy term. Therefore, you immediately see that if you do a Galilean transformation in the real universe in which we live in, you automatically get time dilation and all the relativistic factors, 1 minus v square by c square, plus you also get the anisotropy which you see. So Galilean transformation is the right transformation, not Lorentz transformation, as I have explicitly shown here. And the only thing I want to stress here is that once you say it is Galilean transformation, we have an absolute frame. We have absolute velocity. So the entire philosophical basis which was constructed after the special theory of relativity collapses. We get back absolute velocity and absolute time. So the real clocks, what we thought as a clock moving in empty space goes slow, is not the right situation. The actual situation is the clock is in the presence of all the matter in this universe. When a clock moves, it is moving in the presence of all the matter in this universe. When a clock moves, it is moving with gravitationally interacting with every galaxy in this universe. It is not moving in the empty space. And that is the reason for time dilation. And that depends on the absolute velocity, not on the relative velocity. Once you see that, you can easily explain why certain clocks go faster and certain clocks go slower when they are moved in the presence of this matter. I don't have time to go into details, but later anybody can discuss. I will show you the formula. Okay. Now, I want to spend a little bit of time. Suppose we want to calculate the gravitational potential in this room. How will we calculate? We will say Earth is there, Gm by R. I calculate the potential. But if I care to calculate the gravitational potential of the sun in this room, you will immediately say that it is larger than the gravitational potential generated by the Earth. The gravitational potential of the sun in this room is larger than the gravitational potential of the Earth. Force is larger, other way, but potential is larger. The gravitational potential due to galaxy is a million times 10 minus 6 relative to 10 minus 9 of Earth. So the trend is clear. Distant matter is more important for gravitational potential. So you can calculate the gravitational potential of all the matter in this universe. It is possible to do this calculation. Again, I'm not going through details. I want to stress that when you do this calculation, the gravitational potential of all the matter in the universe is numerically equal to square of the velocity of light. It's a very well-known fact. Therefore, what we thought in relativity as 1 minus v square by c square, the velocity of light, c square, it is not that, well, it has nothing to do with velocity of light. It has to do with the gravitational potential of the universe. It is 1 minus v square divided by the potential of the universe. Relativity is controlled by cosmic gravity. This is a theory of cosmic relativity I have been talking about for some time. And I want to show you how much time, 10 minutes or something? 5 minutes, okay. So now I want to show you, I have been talking about what I think about relativity and so on. What I want to show you now is a fundamental question asked by Albert Einstein himself and answered, and which formed the core idea of special relativity and comparison of clock. The question is this: are two events A and B, which are simultaneous with reference to one reference frame, also simultaneous relative to another frame moving relatively? This is a very famous question which was answered by not only Einstein, before that Poincaré, Lorentz, and various people in different ways. So, let's look at an example. Let's look at an alarm clock where sound is a messenger of the event. So we know the velocity of sound is Galilean. It depends on the motion of the observer. Let's take that example. Sound emitted by the alarm clock moves forward independent of the velocity of the alarm clock. The velocity of sound does not depend on the velocity of the source. In fact, velocity of no wave depends on the velocity of source. But we know that velocity of sound depends on the velocity of the observer. It's Galilean. So even if the clock is moving, it's the same velocity. Now, let's try to answer Einstein's question, assuming that we are using sound as the messenger of the event, not light, sound, which is Galilean. The velocity depends on the velocity of the observer. Now, if the observer is right at the middle of two clocks like that, then two events will be simultaneous for the observer. The sound will reach simultaneously at the midpoint. However, if there is a moving observer, on a boy on a bicycle, we know that in his frame, the sound velocity is more from one direction than the sound velocity from the other direction. The velocity of sound depends on the velocity of the motion. And therefore, the boy will listen to these two events not as simultaneous, but as succession, right? So, we have already answered the question asked by Einstein, if velocity of sound, velocity of the messenger is not an invariant, like sound. The answer is this following. Two distant events judged as simultaneous by one observer will be perceived as successive, not simultaneous, by another observer when the relative velocity of messenger wave is Galilean. Now, if the velocity of sound were constant, suppose it were constant, then of course our conclusion would change. Independent of the velocity of the observer, two events simultaneous to one would have been also simultaneous to another. It's right, it's very obvious, very simple argument. So Einstein asked this question about light, not sound, when he assumed that the velocity of light is an invariant independent of the motion of the observer. So if he assumed that, his conclusion should have been just like velocity of sound being constant, two events simultaneous to one observer is also simultaneous with respect to any other observer. That should have been his conclusion. However, you see, you can verify in Einstein's 1905 paper as well as his famous book on relativity, 1916, where he says, observers who take the railway train as a reference body must therefore come to the conclusion that lightning flash B took place earlier than the lightning flash A. Events which are simultaneous with reference to the embankment are not simultaneous with respect to the train and vice versa. So he arrived at the wrong conclusion after assuming that the velocity of light is a constant. He made a fundamental fatal error. And I was not the first one to point out this particular inconsistency. This was done by the very well-known philosopher Henry Bergson already in 1922 in his really beautiful book, Duration and Simultaneity, which I advise people to go and check and read. You can see during his 1922 visit to Paris, Bergson pointed this out. How did he point it out? Let me show that. Bergson says, after quoting Einstein's passage, he says, this passage enables us to cast on the wing an ambiguity that has been the cause of a good many misunderstandings. Let us emit two flashes of light. The point from which they set out no more belong to the ground than to the train. The waves advance independently of the motion of the source. It then becomes evident at once that the two systems are interchangeable. what is simultaneity with respect to the track is simultaneity with respect to the train. It's exactly opposite conclusion Einstein arrived at. Einstein made a fundamental error, and special theory of relativity, not only because of this, because of all this independent empirical evidence I am presenting, is incorrect. Now, I want to just close with not with the details, because if there is some question, I will come back to it. Many people think that there is experimental proof for the invariance of the velocity. Typically, if you ask the question, what is the experimental proof that the velocity of light is an invariant? People will say Michelson-Morley experiment. No, Michelson-Morley experiment was done some 20 years before the postulate was advanced. The Michelson-Morley experiment is a two-way experiment. Light goes and comes back. So it doesn't measure really the one-way velocity of light. To really verify whether the velocity of light is an invariant, you need to measure the one-way velocity of light. And it's a very difficult problem because synchronization of clocks is involved. And synchronization of clocks are very, very difficult because you have to define simultaneity. And Einstein made the fundamental error in even defining simultaneity after assuming velocity of light is an invariant. So, on the whole, the result is the following. Let me show the result, because I should finish in time, and then we can discuss something. I recently measured the velocity of sound as well as velocity of light using the same kind of experiment. That's two experiments in the same configuration. I measure velocity or one-way velocity, relative velocity of sound. There is another experiment of the same configuration where I measure the one-way relative velocity of light, so that I can compare the behavior of sound and light without depending on a theory. This is the result of the relative velocity of sound. As you expect, it is Galilean, c plus or minus v. The velocity depends on the velocity of the observer. Now I can do the same experiment with the light in the same configuration, and this is the result of light. Let me show a comparison. On the left, you have the relative velocity of sound being measured, and on the right, you have the relative velocity of light being measured. Both experiments are identical in configuration, and you can see both results are identical. Both of them depends on the frame. The true relative one-way velocity of light is Galilean, not invariant. So with this proof, we know that there has been urgent renewal, urgent reassessment of the theory. I will claim that we are in the same situation as Copernicus or Galileo and so on, where we should be intellectually very, very worried that we are holding fast to an incorrect theory of dynamics and relativity, which has been our theory for 100 years. It is nobody's fault, but we didn't have the advantage of the knowledge about the cosmology. And now we have that knowledge, and now if we are blind, we don't see this, then we are only to blame. We should think about it and change the theory. This is a time to renewal. Thank you very much.
Thank you very much.
Okay, ladies and gentlemen, I will tell a little bit background of this my presentation. So, I think you know, everybody saw that in the beginning of or early last century, Hubble invented so that space is expanding. So he measured redshift of galaxies and also calculated distance, and he found out so that galaxies are moving faster away from Earth when the distance is larger. Now, of course, this measurement technology, this has been improved a lot during the years, and now this Hubble telescope is measuring this by measuring brightness of supernovas and the redshift of those. And so this accuracy is pretty good, so that those measurements can be done to up to hundreds of millions of years. So now I am asking, is solar system expanding? So how we can do measurements down to hundreds of millions of years back? So I think the answer is obvious. So we need help from geologists. I will tell about how. So this my outline of this my talk is so that first I define this my problem, and then I look three different phenomena: faint sun paradox, number of days in the year back to the 100 million years, and increase the Earth distance to Moon, and then conclusions. So the definition of this problem is so that established theories, they advise so that gravitationally bound systems don't expand when space is expanding. I think there is no evidence for this claim, but this claim is important part of, I think, standard cosmology. So, but there's a second opinion, not I cannot say opinion, but calculation. So according Tuomo Suntola, theory tells so that solar system or gravitationally bound systems, they expand. So this is interesting situation because of course both claims cannot be true. So and finally nature is of course, because we are talking about physics, nature is the final court. So I will try to study this. So, like I said, we have to study this local phenomena and with help of geologists, because this expansion rate is obviously very slow. So, here. And let's go first to this faint sun paradox. Earlier I have given talk maybe 10 years ago in this society meeting, and I go shortly through this. So, we know so that sun is slowly developing, so that luminosity is rising gradually, and this is very well known by astrophysicists. So that 4 billion years ago, luminosity was about 30% lower than now. But we know so that from geologists and also so that life has existed here, so that we have had oceans here 4 billion years ago. Even this sun was not radiating so strongly. This was first, I think, pointed out this paradox by Carl Sagan, it maybe 40 years ago. And this paradox is coming, it's not solved, and this is coming even worse because of Mars. Now, because Mars has studied by those rovers there and samples, etc., more carefully, now it is known so that there have been oceans 4 billion years up to maybe 3 billion years ago. And Mars is very deeply frozen now. How it has have been oceans when the sun was so much cooler? This is this faint sun paradox. So shortly, some history of this our solar system. This sun is 3.5 billion years old, and very quickly, when solar system developed, so Earth is almost not much older than Sun, and oldest mineral here are 4.4 million years old. And life existed rather quickly. So now, what is at the moment so-called habitable zone around Sun? So if you look, habitable zone, there's a little bit not necessarily very accurate those what is this inner and outer distance what belongs to this habitable zone, but those numbers I took this from one NASA pages where they said this is area where water we have flowing water. It's not frozen and not evaporating. So we see so that only Earth is in this habitable zone. Mars is too far and Venus too hot. So I told about so that luminosity will change. There's good studies of this, and we have had this water here practically. Temperature has been on the Earth very long time, rather constant. So this explains more detailedly this Feynman paradox, but I explained this already so that now Mars is currently very frozen, and so this is pretty cold now. Average temperature is -60 and lowest -140 at the moment, and you can imagine so that what has been when luminosity has been 30% lower. And there has been oceans there. This is a big paradox. So, and the atmosphere now is 1% of Earth's atmosphere now there. So standard cosmology tells so that space is expanding, and the expansion rate will increase, and the gravitational bound don't expand. But let's think so that however, if solar system is expanding, so I calculated what, according Hubble law, I calculated what were distances when life appeared on Earth. So Earth was 0.77 astronomical unit closer, and Mars was 1.19 astronomical units, and using same definition of habitable zone, I calculated what is this, and you can see so that Earth is just in habitable zone. It is a little bit hot, but also Mars is in habitable zone. So according to geology, they tell so that oceans at this time there was warmer than now, maybe about 40 centigrade or so that life was possible there, but it was not evaporating. But it's warmer than now. So I think, any case, this expansion of solar system, there is no conflict with this explanation for this faint sun paradox. But let's look what we can have more. Okay. So I have one comment here, because those astronomers or astrophysicists, they claim so that Earth cannot be any more habitable after maybe 300 million years, because the temperature of the sun is rising and rising, and after 5 billion years, oceans will evaporate. But this is amazingly short time compared to this total time what life has been here. So I think this Tuomo promised me several billion years more for life on the Earth. So okay, let's go to second one, where we need, okay, so geology was needed also to explain what has happened on Mars and on Earth. But let's look this number of days in a year. It is known, of course, it has been known a long time, so that tidal friction will slow down Earth's rotation, so that rotation number in a year has been large. So there are more days in a year. So, there have been many studies, theoretical studies, what is the rate, slowing down rate of the rotation. And I found recent paper 10 years ago, and this was calculated. So the tidal friction will cause 2.5 millisecond slowing down of rotation in 100 years. This is pretty close what the people are calculated from angular momentum decreasing of the Earth, and this compensating by distance of Moon. This is like a starting point, but let's go how this has been very accurately calculated. What has been number of years, hundreds of million years ago. So the corals, they are growing so that they grow like you can see like a daily rings. Like in trees, you can see these yearly rings, and you can calculate how old this tree. But corals, you can see this daily layer, so that if you have fossil of coral and you lap this and you look under microscope, you can directly calculate number of days. And the year you can see because winter is less light and water is colder, so that you can see variation of the thickness, so that you can pretty accurately you can calculate how many days has been in a year. And then radioactive dating will tell the age of the fossil. So those people, they have done very, very, very good work. And so the history, they have studied down to 800 million years ago. And at this time in a year was 435 days. Now, but what was the length in time, the year? Then we have to go to the theory, because this number is absolute, because you just count those. But then we have to come to the theory. And current theories assume so that the year in seconds has been same than now. But this is theory, but let's go ahead. So I think, I took this formula from Tuomo's book. I collected this literature, this coral data, and then Tuomo fitted those in his model, this data. And this was rather interesting, because in addition of this just tidal friction, you have to take account of this orbit, how the orbit is growing. And this is formula, and I saw his result. So this is first those points here. Those are experimental points from those scientists who calculated the days from the corals. So this is very, very good experimental data. And the calculated, this tidal friction gives too high numbers of days. So when Tuomo applied his model, so how orbit is growing, he nicely made very nice fitting. So I will go back to this formula, because this is pretty interesting. Because here this delta t is the time past what we are looking. And t0 is time from the origin of the universe. And in his theory, this t0 had this direct connection to the age of current theory, this 13.5 billion years, but this must be multiplied by a factor of 1.5. But it's mathematically directly connected. And this t0 is also directly connected to Hubble constant. And if you calculate what Hubble constant comes from this t0 when you have the excellent fit, you will have Hubble constant 70. I think it's rather surprising. So that observations in the Earth can give right Hubble constant. Okay. So, and let's go to the last one. This increase of Earth's distance to Moon. This also has been known, of course, because angular momentum will decrease, so same time angular momentum of Moon will increase. And the distance of Moon has been measured now very, very accurately. Astronauts set mirrors on Moon almost 50 years ago. And so since then, this distance has been measured, and now is measured so accurately so that this distance to Moon will increase 3.82 centimeter in a year. I think it is very surprising, but this is so. So Tuomo calculated so that from this 2.75 comes from expansion of space, and tidal friction is about 1 centimeter. So, but the mirrors on Moon, this is not the only way to measure this retreat rate of Moon from Earth. And also we need help of geologists here. So tidalities, they cause deposits in several places, like sand layers. And so that nature has like an archive of those lunar cycles. And especially there's very good formation in Australia, in sandstone. They have drilled this, and there is continuous 60 years layers of those. And those layers thickness, they vary, because you know, so that tides, when Moon and Sun are same place, you have higher tide, and so you can see this periodicity in tides. So it is possible directly calculate those layers, how many time Moon has rotated over the Earth. So this is again pure number, this result, so that not any theory dependent, but direct number. Okay. And now, if you know, because now you, from those, you know what is the time of Moon orbiting Earth. If you assume the year length is same, you know the number, you can calculate the orbiting time. And from Kepler's law, you can then directly calculate what is distance of Moon. So geologists they have done good work, and they have published results based on this assumption. So, but I studied this a little bit more closely. So first I will give two results, so that this Australian deposit which is best. So average rate, retreat rate is 2 centimeter in a year. And in United States is also one deposit, but not so long and a little bit more different to interpret what is number of rotation. But pretty good result, so that they have got result 1.46 centimeter, and these error estimates are much larger. I have not put it here, but those are, and those, this is pretty accurate, this first one. Okay, so those sediment results, they give 50%, around 50% lower values than what is direct observation. And the weakness in those calculations is again so that this length of the year is assumed to be constant. So I came back also to look Tuomo's model, and because I can calculate this in seconds, what has been this length of the year, this 600 million years ago. And let's go what we'll have. This is this number what he has calculated, so that clock rate in the observable clocks will change on the Earth 2.3 milliseconds in the year by atomic clock. Okay, so results are rather interesting when I applied this Tuomo's model. So this Williams, this Australian deposit, I got number 3.98 centimeter in a year, and this US deposit 3.57, and this modern value is 3.82, so that those both are very well in error limit of those measurements of the geologist. So I think so that I'm pretty much convinced so that this there has not been any sudden lowering of the moon, so that it's continuously moving. Of course, when you go billions years ago down, it will change, but those are, I think, rather convincing results. So I studied those three phenomena and 3 to 0, so that those prove so that the gravitationally bound system will expand when space is expanding. So I have some discussion, maybe I will leave to Tuomo, so how this is possible, so because now it has been very difficult for current theories to understand how it is energetically possible so that those can be expanded when space expanding, because a lot of energy is needed when moon is, of course there's this distance will increase, but of course this tidal will help this. But in any case, by current theories it's not possible. And I would like to mention this, what Unni said, so that we have to remember so that potential of the whole space is huge, and this expansion of space is huge phenomena, so that this local gravitation, their potential is very, very small, like we can see and know from physics, so that the inertia of the mass, this is not, this is completely independent on the mass of Earth and Sun and the Milky Way, and also we know so that the Coulomb pendulum keeps its frame regardless of rotation of Earth and Sun. So maybe I will close my session.
Thank you, Heikki. I think we'll skip the questions again and give Tuomo a chance to close up the morning session. So our next speaker is Tuomo Suntola, and as you see from here, the Millennium Technology Prize. Let's give applause to Tuomo. Little late one. earned anyway.
Thank you so
Tuomo,
much.
please.
So, ladies and gentlemen, I titled my talk as Unification of Theories Requires a Postulate Basis in Common. So let's start from this present situation here. So that's the big puzzle we are facing today. The different branches of physics have very different package of postulates and basic definitions, which partly don't interfere with each other, and some of them may interfere with each other. We are not going through all of those because it's a real big package, but let's see the very fundamental properties here. So the three of these parts in our puzzle honors conservation of energy, but in fact the rest two parts ignores the conservation of effect, which I feel is probably principally the most serious infringement of the unification. If we start working with the reasons behind the problem, we can first identify one very important reason here in relativity theory, both special and general relativity. So special relativity is based on relativity principle, which means, for example, that the observer in general can look his location as a state of rest for the observations he is making. And equivalence extends the relativity idea to gravitation based on equivalence principle. So let's look about observer-oriented reality or system-oriented reality. What kind of differences we can find in these two? Historically, perhaps the most obvious and well-known example comes from antique observations of planets which didn't fit with circular orbits, and the conclusion and the solution was here. Eudoxus, who is the father of the epicycle model, considered epicycles as simply a geometrical tool for the illustration of planetary motions. However, the great philosopher Aristotle, in his Metaphysics, describes Eudoxus' model as the real mechanism of planetary motion. So Aristotle thought that really the planet makes all those epicycle rotations. Well, let's come 2,000 years later, and in late 1800, observations on light and fast-moving objects didn't fit with linear space and times, and the solution was here. Distorted time and distance as the explanation for the relativity of observations are considered as real properties of nature. I found a citation from Einstein's lectures in Berlin in 1911, where he explains the problem of the time dilation and the distance differences. So length contraction really exists insofar as it doesn't exist for a co-moving observer, though it really exists in such a way that it could be demonstrated in principle by physical means by a non-co-moving observer. I think it should be read at least twice or three times in order to understand the real message, but the logic is there anyway. So that reality looks different for an observer when he looks phenomena moving relative to him, and when extended to the gravitational effect, also the similar difference can be found in gravitational systems. So, what was the way out first from the Ptolemy astronomy? And clearly it was by setting Earth as the center of the Ptolemy astronomies, they lost the structure of the planetary system and the observer's motion in the system. And the answer was Copernicus introduced a system-oriented perspective of the sun and the planets, which uncovered the effects of observers' location and motion in the system. So the observer now took an external observer's position, and which makes the system easier then to understand. And that was extremely important for the further development of physics, so that it led to Newton's laws of motion, and in fact it led to the start of mathematical physics in general. So what we have to do now is the next step indeed. So instead of looking the planetary system only and have an external or let's say a system-oriented view on that, we need to have a system-oriented view to space as whole. So we are now looking for a system-oriented perspective for whole space in order to reorient ourselves in the system and uncover a possible hidden motion we are subject to in the system. Okay, and to go into that, we first need to pay attention to the coordinate systems. We, in fact, need the metric fourth dimension for closing space as a three-dimensional surface of a four-dimensional sphere. So that in order to look energy system, we need a closed system, because then we can apply conservation law for energy and some key properties as well. So that in the theory of relativity, fourth dimension is considered as the direction of time, so that it makes it very difficult to consider this kind of geometry. Even if that happened, the first idea of Einstein himself of the cosmological structure of space based on general relativity was just the idea of spherically closed system. There were major problems in that, because at that time it was generally understood that space as whole is a static entity, so that when he saw that if there is mass in a surface of a sphere, it must collapse, and then in fact is why he added the cosmological constant in the as an option to the theory, which now was recovered as dark energy to match the recent observations. So what we do, we now close space as a surface of a four-dimensional sphere, so the surface itself has three spatial dimensions. It means that a mass point anywhere in the space is affected by the mass of the rest of space, so it's subject to the gravitational potential created by all the other mass. And due to the geometry now, when it's close to the fourth dimension, it can be easily understood that the center of such much of the mass representing the rest of space is in the middle of in the center of the four-dimensional sphere. So it's not in space itself, but it's in the center of the structure. Now we have gravitational force between any mass m in space and the mass equivalence of the rest of space. In fact, it could collapse, which created some momentum and velocity towards the center, or other ways round, it may be in expansion, so that the motion of the expansion is balanced with the gravitation of the system. And denoting the energy of motion here in the same form as we are used to describe the electromagnetic radiation. It's velocity times momentum. In this case, it's mc to the second. We get zero energy. We can consider a zero energy balance like we have in the pendulum. So pendulum has first potential energy, it releases potential energy, gets its velocity of motion, and then gives it back. When we look at a spherical pendulum, the situation looks like that. First, we start from a large sphere with mass homogeneously in the system and let it contract. So it goes into a singularity and then start to release the energy of motion back to the energy of gravitation. So it looks like this. We get the energy of motion against the release of the energy of gravitation. So it's kind of loan for expressing energy through the energy of motion. And we can identify this energy as the rest energy of mass, which is all the time balanced for any mass particle in space with the gravitational energy raising from the rest of space. When we equate these two energies here, we indeed get the velocity of expansion, which according to our formula for the energy of motion has the value of the velocity of light, which is plus minus the square root of the gravitational potential, as also Professor Unnikrishnan stated in his talk. In fact, it turns out that the velocity of space in the fourth dimension determines the maximum velocity in space. So in fact, once we have the same velocity in space as the space itself in the fourth dimension, the object moves like on a satellite's surface, so that it's in a kind of weightless state where the velocity of light propagates in space. So let's summarize. In the standard model, the energy of matter in space was created in a quantum jump. And it's generally stated that it probably is against release of unknown quantum potential. Anyway, it is unexplained phenomenon, and in the dynamic universe we have certain development. Let's put the pointer here. Here we go. There's a similar development before the singularity here, and then we have the expansion, which is now defined by the energy balance between the energy of gravitation and energy of motion. So we don't need to speculate with the velocity of the expansion, because following the zero energy principle, we know it precisely once we know the radius we are today. So it means that the rest energy as matter is the energy of motion obtained against release of gravitational energy in the contraction phase, as I already stated. So some consequences of that is that in standard model, as Heikki explained in his talk, space is expanding. Local systems like galaxies and planetary systems conserve their dimension. And that's a conclusion that originally made, very originally, the earliest one I found in the literature was by De Sitter in early 1930s. And after that, it has been taken as a fact. And let's go further. In dynamic universe, because everything is related to the rest of space, all gravitational systems are part of the total gravitational system, we can say the whole space. It means that local gravitationally bound system expand in direct proportion to the expansion of space, and that's what gave the nice results in Heikki's analysis of the planetary system. Next is very interesting, because the velocity of light and the rest mass of matter are conserved and considered as natural constants. That's very important part of standard cosmology, and not only cosmology, but standard physics and the theory of relativity, including the theory of relativity. In dynamic universe, the velocity of light is linked to the velocity of space in the fourth dimension, and the rest mass to motion in space, which we come a little bit later back to this, why this is the case. And very important consequences of this postulates is that the reduce of this postulate of the constancy or velocity of light and rest mass is that the reduced frequency of atomic clocks by motion and gravitation is explained with dilated flow of time. And in the case of a dynamic universe following the energy balances, we can now explain the reduced frequency atomic clocks by motion and gravitation by quantum mechanical solution of the characteristic frequencies. So we don't need any further postulations here, because today we have the atomic clocks and theory which very accurately tells the frequencies. We also come to this a little bit later. Let's now look, now we found that any motion in space is linked to the motion of space, so that there's no independent motion in space. Any motion in space has the motion of space as the orthogonal component. So for object at rest, we only have momentum in the fourth dimension. And that's why, once again, it's very important to understand that the fourth dimension shall be understood as a metric dimension. Otherwise, we couldn't have momentum and velocity in the fourth dimension. And then, as stated already, the velocity of light, the momentum and kinetic energy or energy of motion or electromagnetic radiation now has the same form, so that now each energy's motion can be expressed as c times momentum, as we also have here. And what happens then when we are combining a velocity of a mass object, velocity lower than the velocity of light? We all know, at least those of us who have read the special relativity, that the total energy or energy of motion expressed with this formula, it's c, velocity of light, times mc, which is formally has the dimension of momentum, and the momentum in a space direction. Obviously, we can write that in complex form, so that we understand mc as the momentum in the imaginary direction, and momentum p, momentum in the direction of real axis in space. And now we have exactly the same formula for all energies or motions. Let's look at this graphically. So we have the mc, an orthogonal component, the velocity in space in the direction of real axis here, and the total momentum now is the sum vector of these two orthogonal vectors. Analyzing the structure of the total vector, we can identify the mc, the rest momentum part, and an additional mc, which is the momentum added for obtaining the motion, or let's say, which represents the kinetic energy, the energy of the motion which has been received from the accelerating system. We can now see that also the momentum comes from two orthogonal parts. So momentum in the direction of real axis, it has the part mv, which comes as a real component of mc, and then the additional part representing the share of kinetic energy. The interesting conclusion here is that once we have given mv to the momentum in space, we have reduced rest momentum in the object at motion. And that's extremely interesting also in the sense that that's now the momentum which is balanced with the gravitational energy. And once the mass is reduced, it also means that the gravitational energy from the mass equivalence from the rest of space. Now we have obtained the balance, and we can notice that the imaginary component of the kinetic energy and momentum is exactly the work we are making against for reducing the gravitational effect of the rest of the space, which is exactly the Mach's principle. So that when we are accelerating our car, it means that the work we do in accelerating is exactly the work we are making against the gravitational energy of the rest of the space. So we are communicating with the whole universe in all our daily activities. That's what it means. Okay, let's look local phenomena. First, we started from a homogeneous space, and having a local space, we have the big build-up of momentum. But for that, we need collecting some energy from somewhere else, from our neighboring systems. And that's why, as we noted in the preceding slide, our rest energy in the state of motion has decreased with this square root 1 minus v divided by c to the second power. But how about gravitational build-up of gravitational centers? It means that we need to maintain the balance, and maintaining the balance means that now, instead of putting more energy to observe the motion, we have received the energy against the reduction of the local momentum or local rest energy in the local fourth dimension, which is twisted here, and we can see that a component of that's the way we have obtained the velocity of free fall in space. So the mechanism is different, and this different has very important consequences then when we look for celestial mechanics and some other phenomena. So now we can relate the reduction of the velocity of light close to the mass center to the gravitational potential of the local state here. And it means that the total effect of motion and gravitation on the rest energy is now illustrated with this formula. It has the gravitational term and the term resulting from local momentum. In fact, that kind of mass center build-up occurs in several steps in space, which means that we have much more complex structure, and in each case we are collecting mass, which means also bending of light, building up a dent in space around the local mass center. And it means that putting everything together, we need to take into account all the gravitational and motional system we are subjected in space, and it shows that the distance to the homogeneous space, the kind of absolute frame of reference, which also Professor Unnikrishnan was looking for, can be found by following the energy structure of space here. That the more anytime we are binding ourselves to a local system, we bound some part of our energy to the system, and we have less available in the local state. But at the same time, we can find that locally we can look velocities and energies in the local system by using the reference of the local state of rest in the system, which makes this formula look identical with that of special relativity. Okay, we can also easily understand now the behavior of the velocity of light, which is linked to the local 4 velocity of space. We have a big dent around the sun, and each planet has their own dents, and when the dent with the Earth orbits around the sun, we can also see that the reference for the velocity of light is following the rotation, the orbiting, and it explains why important observations for atomic clocks and the test of relativity follow the Earth-centered inertial frame. Back to the bustle. So now we made major rearrangements in cosmology and general and the relativity sections here, which means that in cosmology we accepted zero energy principle in spherically closed space, which solves the energy build-up in space and discloses the system of nested energy frames, which are extremely important then for understanding observations. In fact, we can ignore the basic postulates behind relativity theory, and in fact we don't need a separate relativity theory, because as soon as we take into account our velocity with space and the effect of the rest of the space, the relativistic effects come automatically, so that we can live with these. Our next task is to look at the two sections, quantum mechanics, electromagnetism, and perhaps the most illustrative thing is to compare Planck's equation for the energy of electromagnetic radiation and the power of an antenna emitting electromagnetic radiation. I can't go into the details here, but this is the solution which we can find in any textbook, on a physics textbook, so there's nothing new physics at all, but we can rearrange the constants here and relate the length of the dipole to the length emitted, and then look some simplification by thinking about the energy emitted one single cycle of electromagnetic radiation. If I ask a radio engineer what probably could be the smallest amount of electromagnetic energy, he probably say that it must be the energy emitted by a single oscillation cycle of one electron in a dipole, and that's what we are going to demonstrate here. But further, we replace the Hertzian dipole geometrical factor with about 1, and we end up with equation which now opens up the Planck constant. So with this practically isotropic geometrical antenna, which you can consider as a point emitter in space, because in one cycle it makes a distance of one wavelength. It has the velocity of light. And it means that it's very useful to pick up, we find that there's also the velocity of light as a hidden factor inside the Planck constant. We take it out, and we can now rewrite the formula in the form intrinsic Planck constant without the velocity of light, and once we divide that with the wavelength, it has the dimensional kilograms, and what is left is then the velocity of light to the second. So basically the formula has the form of mc to the second, exactly the same as what we have for rest mass of electron. And that's a very important part of the unification. Now we have completely unified formulation of the energies of motion, and we also have that connection to the gravitational energy through the balance of motion and gravitation, which means that it covers now the whole structure. And we can go back to our puzzle and solve our puzzle with this improvement. There are very important consequences also to the interpretation of the quantities in quantum mechanics. It doesn't change quantum mechanics. Quantum mechanics works exactly as it does today, but it may give some new understanding behind wave function, what's the nature of wave function, and many other properties of that. We don't have time to go into that, so I'm afraid that Sherman very soon comes and asks me stop. But let's say looks still the frequency of atomic clocks. So this is the quantum mechanical formula for the frequency of atomic clocks. Now the first step we do, we replace Planck constant with the intrinsic Planck constant times the velocity of light, which makes it possible to remove one velocity of light. And now the frequency clock is proportional to the rest mass of electron, which also means that it comes a function of the state of motion. It's proportional to the frequency, to the speed of light, which means that whenever we measure the velocity of light with an atomic clock, it looks like being a constant. So that this is what Professor Raimo Lehti called the conspiracy of the laws of nature. So that if our measurement system follows the same physical basis as the phenomenon measured, we can't find any differences. Very important result from that also is that now in quantum mechanics, important factor, which is the fine structure constant, becomes a numerical factor only. So it's not anymore connected to other physical factors. So we now have our frequency formula for atomic clocks, and this is the similar corresponding equation derived from the general relativity, and in the vicinity of the Earth, in near-Earth experiments and ground experiments on the Earth, the difference between these two expressions comes only in the 19th or 18th or 19th decimal, so that all measurements accuracy we make exactly the same. When we approach local singularities, then the situation is different. I don't go into the details, but I simply state that starting from Michelson-Morley, the famous early experiment, and all the following test arrangement for testing the relativity theory, finds now a very simple, straightforward solution without any twin paradox or any other paradoxes, but they can be simply stated that the frequency of a clock is the function of the local gravitational, the state of gravitational motion and the state of motion and local gravitation, which makes life much more easier and understandable. Let's have a very quick look to the law of motion, the second law of Newton. Now it's to be studied from the total energy formula, and we solve the force as the time derivative of momentum, and we can find that the equation looks a little bit more complicated. But when we look, what are the effects? Now we have the effect of local gravitational state on the velocity of light, effect of motion on the rest mass, and finally the effect of local motion on the relativistic mass, the same factor as what we get through special relativity. When we eliminate the two first effects, we get the result of special relativity, and when going further, we come to Newton's law. But as we can see, we can't get the total effect of the rest of space by starting from the local formula represented by Newton's law of motion and also special relativity. Now I simply state some cosmological consequences here. First victory of general theory of relativity was the perihelion advance of planet Mercury. So it's the 42 arcsecond per 100 years, which was known already in mid 19th century. When we use the same formula, which is one typical solution from one of the astronomy books, we can find that it leads to instability close to a black hole when we have very high gravitational interaction. So these were very nice results. The bad news here is that if we follow there is one factor which is cumulative, which means that if we follow Mercury for 300,000 years, also the same happens to Mercury. So the same equation results the instability close to black holes, but with time it will make the same for planets with smaller gravitational interactions. The corresponding formula, when we follow the conservation of energy, so full stability down to the critical radius. We simply state that the stability which we find by following the conservation of energy also results in a nice agreement with observed rotations, short rotation periods at Sagittarius A, which is the big black hole in the center of our galaxy. So that the instability of Schwarzschild solution here doesn't come to that part, but with this we can solve the problems. Okay, I simply state some. Heikki already showed the effects and some of the important conclusions in planetary scale, but we look some of the cosmological consequences. So according to standard model, these are the dots here are galaxies and quasars, and the picture illustrates the angular size of galaxies and quasars as a function of their distance, which is measured in terms of redshift. So the prediction of standard model, which is the equation here, should place the observations between these lines. When we add the dark energy here, it doesn't change the situation much. But when we solve this from the dynamic universe, where the galaxies also expand together with the expansion of the universe, we end up with a complete match with observations. And the important part also, which Avril already showed as an example of added parameters, when we make the same calculation with dynamic universe, we end up with a very simple formula here, and it is full replacement here without any parameters, and the blue line here or curve here gives a perfect match with observations here. And summary here. Dynamic universe allows an understandable picture of reality with absolute time and distance, and give at least as precise prediction to cosmological observations as a standard cosmology model, and doing that with essentially simple mathematics and less postulates. And also it opens a new perspective to understanding of quantum phenomena. So thank you very much for your attention. We can understand that it's very I would say it's exceedingly ungrateful task to propose a paradigm change of this size, because it means that we have to reconsider years and say thousands and even millions of man-years work. However, the observation, they stay, and we have no risk to consider that reality itself has changed. The reality stays as it is, and our model describes it better or widely or more accurately or less accurately. So it's an ungrateful task, but anyway, somebody has to do it. Thank you for your attention.
Thank you, Tuomo. Thank you, Tuomo. And I like to thank all the speakers this morning for very interesting and rather exciting talks.
Hello, everybody. Welcome back. Next speaker is Valdi Ingthorsson, yes, from Lund University, also known as the Unifier from Iceland. His topic is Ontological and Methodological Reflections on the Virtues of Unification.
Yeah, hello. So, thank you. Yes, I'm going to be talking more from the perspective of philosophy, trying to, in a way, offer some ideas about why unification could be interesting, not just for physics, but also for philosophy, basically in general, and which might, in a way, talk in favor of unification regardless of any problems with physics or whatever solutions are being offered and so on. Okay, it's more about the idea of unification as a good method in a way. And I could in a way say that that philosophy is in a way in a similar state of, as I understand, disunification, which maybe strangely enough coincides perhaps with the growing disunification in physics. Throughout the 20th century, philosophy has gone through a number of revolutions regarding what philosophy is all about. And people have been, in a way, in a certain sense, a little bit fascistic about that. Either philosophy, the only thing it can do is to clarify language. So we have all philosophy of language. Or the only thing we can do is to illustrate some concept of knowledge, perhaps. Everything becomes epistemology. And then other people say that metaphysics is the only way to do things, and so on. Instead of looking at the different disciplines as sharing the burden of understanding the total picture, in a way. Okay. So there's a point of also advocating unification within philosophy. But the focus here is perhaps on how metaphysics perhaps and physics could in a way combine. And on the surface of it, metaphysics seems to be engaged in a very similar kind of project. It's often described as seeking the answer in a very abstract and general way about what there is, what it's like. Sometimes those are distinguished into ontology answering the first, metaphysics the second, although I find it difficult to see how you could really answer one without answering the other at the same time. Right? So I tend to say I'm doing metaphysics, encapsulating both ontology and metaphysics. So there are questions about existence, objects and their properties in a very general sense, space and time, causation, which is my kind of field, necessity and possibility. And if it hadn't been for the possibility there at the end, I think we'd be, in a better position because possibility encounters all kinds of, or generates all kinds of questions about, well, if things could be differently than how they are actually, how far can we push that's different? So if we start with the assumption that metaphysics and science are in a way continuous in the sense that they're trying to answer the same question, both are trying to figure out what the world is really like, as opposed to what it appears to be like, that invites the metaphysical speculation or hypothesis about underlying structures and so on. Then the question, what is this reality that we're talking about that we initially seem to be investigating? Is that equivalent to the world or the universe as we know it in a way? Is that in a way the end point of understanding the universe? Well, in some circles, in philosophy at least, the assumption is that's not the end of reality. Is much bigger in a way. Being is wider than just the universe as we know it. And so for them, whatever physics finds out about this particular world is just to find out about one among many possible worlds. And therefore the theories and findings of the empirical sciences just aren't really interesting or relevant because you're only telling us one side of the story. On the other hand, you can wonder, well, what constraints do we have then for any thoughts about this larger reality? And in the end, it becomes just conceivability. Everything that is conceivable is then actual component of what we could call the ultimate reality. And in philosophy, there's no check about which of these many conceivabilities are in a way actually real. And you can wonder, as I wonder, whether that really is an exploration of reality or just an exploration of the limits of thought. And if that's the case, it's only an exploration of the limits of thought. We've not really been doing metaphysics. Okay. One can wonder in physics, what are the limits imposed there? Well, the idea is that there's this world, and whatever we find about this world is the limitation on what's possible, necessary, and so on. We might want to find out certain laws of nature about how the world necessarily works. Doesn't exclude that things could have turned out slightly different from what they actually turn out to be, but it's still an aspect of this world. But I'm worrying also that perhaps in physics we're seeing the idea that the mathematics is what defines reality, and the mathematics is richer than what the actual reality is like. And that invites speculation about, in a way, a broader, general, more mathematical, ultimate reality, of which the actual mathematics of the present universe is just only one instance. Yeah. Maybe there's, in a way, similar things going on there as it is within philosophy. And this, in a way, this separation of metaphysics and science, I see frequently in the media, and this is just one of the very latest I've seen. Science is a method used to discover facts about the material world. Metaphysics, however, deals with the whole of reality, or put in a philosophical language, being as such. Where science discloses the properties of the physical world, metaphysics ventures beyond the physical and explores the fundamental nature of all that is. So hinting at the idea that all that is not just the things that actually exist, but being is somehow wider, right? Although perhaps we can, well, I'm misunderstanding this person, and maybe it's just meaning that that metaphysics is operating on a higher level of generality, and that it's not just physics, but also chemistry, biology, the humanities, and so on that become interesting, the mind, yeah? And that's a completely different scenario, because the mind can be in this world as well, right? And doesn't have to cover all possible worlds in a way. So here's another conception of how metaphysics aligns with physics and still is different. The different particular empirical sciences are looking in a way at different segments of the larger picture. Physics typically looking at the smallest entities, particles, forces that operate between them, space-time structures and so on. Chemistry then, looking at larger compounds, looking at the bonds between them and the reactions they hold. We can move into biology, looking at different stuffs that are more systematic in character, are able to send over genetic material and so on, yeah? And there's nobody in these disciplines that in a way takes then a step back and asks, are there something that cuts across all the different disciplines? Some kind of conceptual structure that they all in a way share in a more generalized way. For instance, do they all assume some category of persistent entities that we call substances, or some even more abstract stuff? Are they all assuming properties that are attached to these substances, relations between them? They assume there's something called causation, and we'd like causation to operate between the particles, between the chemical compounds, between the biological entities. So the role of metaphysics becomes to describe those very general, in a way, or offer a general model of how that can be done. I've offered, for instance, that causation should be understood in terms of reciprocal action or interaction. That seems to be something that cuts across all the different disciplines. And in this sense, yes, we're doing the same thing, but slightly different way. And then metaphysics, in a way, becomes the joining point. And in fact, metaphysicians have seen themselves, or seen metaphysics as, in a way, the spider in the web of science, linking the different sciences together. This is from Jonathan Lowe, saying that metaphysics is an ineliminable and conceptually necessary as the intellectual backdrop for every other discipline, because the world or reality as a whole is unitary and necessarily self-consistent. And note, there are two claims here, one about metaphysics, the other about the world. The claim about metaphysics shouldn't be taken as a claim about the discipline of metaphysics. Metaphysicians that are part of the discipline don't perhaps engage in that kind of thing. Rather that wherever anyone speculates about connections between sciences, tries to link certain things up, makes assumptions on this more general level, they're doing metaphysics. So metaphysics is a shared enterprise among all of us, right? Some just specialize, yeah. So that's in a way, the way we could say that the role of metaphysics is to, in the end, be unificatory, you could say, yeah? Although that's not the way it is pursued in actual reality, yeah? The other claim about, in a way, world being necessarily unified and self-consistent, yeah, the end image, perhaps, or what we're hoping for is to achieve an idea of reality where everything fits together. We can understand how the atomic level fits to the molecular level, to the biological level, to the consciousness, to the psychological entities, and also then the groups of psychological beings and how they behave. We want to understand that as one unitary whole, which again becomes very complicated and difficult, as we can say. But okay, that might be just wishful thinking, that we want to get this unitary image. Are there any reasons that we can find for looking for it, for the unification? And there are certain principles of thought that come to mind from the history of philosophy. One being, or sometimes called the principle of continuity, which is probably another in physics called the principle of continuity, and maybe it has a kind of similar origins. Leibniz favored this principle very much, and it's the idea that nature contains no gaps and takes no leaps. Can be understood in two different ways. The first is that it's difficult to imagine, in a way, reality as being fragmentary, that there are kind of parts of reality that bear no connection to anything else. That seems to be an idea of those parts just not being a part of the world. At least not a part of the world that we could know about. Yeah? It's kind of per definition. That's the things that we're never going to find out anything about. The other, that it takes no leaps, has to do with this idea that if something is in a certain state and changes from that state, it has to, in a way, go through all the intermediaries. If something moves from a certain velocity to some completely different velocity, that looks like magic. Yeah? So we want them to progress through all the different stages. And to do it in a systematic way. It shouldn't do it one way one day and then another the next day. Then we have kind of lost the uniformity of nature. And in a way, the ideas about the uniformity of nature arguably perhaps come from this idea here. Right? So it's the idea of something as one unitary whole. Leibniz, as I said, was fond of it and he used it also almost like an argument. I mean, he thought, for instance, that causation was impossible because of the principle of continuity. He was thinking of the Newtonian theory of motion and the idea that something could move, as he thought, from rest, absolute rest, to motion was a breach of this principle of continuity, because rest is one thing, motion is a completely different thing. So nothing could go from rest to motion, however small the initial motion was. We've later solved that problem by saying, well, there is nothing really at absolute rest. Everything is in relative motion, so causation is possible on that view. Or at least Leibniz's argument isn't a good argument against that. And that's in a way, okay, he wasn't using the principle in the wrong way, he was assuming the wrong things about the world and coming to the wrong conclusion because of that. He could hold on to the principle anyway. Then we have another principle called the principle of ontological determinacy sometimes, a principle that the philosopher MacTaggart, famous for MacTaggart paradox, thought was so fundamental that he called it the total ultimate presupposition. And the idea behind that is basically, first of all, it is a presupposition. It is a metaphysical assumption we make that we haven't proved. Okay? We begin with that assumption, and then by applying it, and we, in a way, find that it leads us the right way, we're successful in applying it, we grow in self-confidence and thinking, yeah, this is the right principle to hold. To say it's the total ultimate one has to do with, well, we can explain the principle first, before we go to that, perhaps. It's the idea that everything always has a determinate state. Nothing can both be and not be in a certain state. And that's an idea that goes back all the way to Aristotle. If we assume that everything is in a particular determinate state and everything is a part of the world, in accordance to the principle of continuity, then in a way it follows that the world as a whole is always in a particular determinate state. And if it has a determinate state, surely it can't be fragmentary. So there's a clear connection conceptually between the two principles. Now, there are certain things we have discovered that might, in a way, challenge this. And that relates to the point that McTaggart had, was that for him, if we don't assume this, then the whole enterprise of figuring the world out just collapses. How could we find anything out about the world if it didn't, or if it wasn't determinate? Because it also follows, of course, that then our thoughts, if we are a part of the world, are not determinate. So we can't know anything, and there's nothing to be known because everything is in an indeterminate state. So yes, we might perhaps accept that some parts of our world are indeterminate, okay? And there are hints in quantum physics. There might be some kind of indeterminacy, right? And maybe we're prepared to accept that, as long as everything else makes determinate sense to us. But to assume that everything is indeterminate kind of collapses the whole enterprise. So there are certain kind of, let's say, it undermines the intellectual motivation that we might have to assume the contrary to this principle. And that's nothing to do with, empirical results or anything like that. It's basically just, do we think it's worthwhile doing it before we have done it? And if we accept this principle, yeah, it seems to be worthwhile doing it. And there are certain methodological consequences from this. If everything is maybe not connected, but at least part of this continuity, then to find out about any phenomenon A is at the same time to find out about its connections to B, C, D, and vice versa, which means that basically to find out about A is to find out about its place in the whole. It also means that if we are finding it difficult to find out about A, well, why not first check out B and C? Because they could give us leads about A, and vice versa. Okay? And that's basically how we're supposed to do it in the hermeneutic circle. You look at the parts, you compare it to the whole, and by going back and forth between understanding of the whole and part, we end up, at least in the end, in some kind of reflective equilibrium. Now it fits, yeah? So, and it seems to me that this idea has been a guiding principle in classical physics, very successful for a long time. Everything was in a way linked up, everything's defined in terms of something else in a certain way. And then it proved difficult to understand relativistic and quantum phenomena in the same way, and that led in a way to, the fragmentization. And that leaves us in a state that, well, maybe the usefulness of the principle of the methodological, this method is kind of come to its limits. Maybe it is the way that as someone has commented in the audience, that maybe the world just is fragmentary. Some things are unified, others are not. Or maybe it's just too complicated. We're finding out it's too complicated. Does that, even if we accept that, maybe it's too complicated, right? We just don't know yet. Maybe it is fragmentary, but we just don't know it. Should we give up? Even if we, consider the possibilities. And I would say, is it time yet to give up on that? That seems to be, in a way, a plan B, right? A little bit of a defeater project, okay? And it doesn't mean that we all have to pursue this project. Some can go for explaining the parts, doing their work in peace, never have to think about the unification. Others can do that. So we have a division of labor between the kind of projects that we have. And in fact, that will probably be the most effective way. We get the immediate results from investigating the parts, and we can slowly, gradually fit them together in a leisure time, yeah? Let's just not forget about that. It seems the focus has been on the understanding just the parts so far. Yeah, let me leave you with one, because in a way, the mind has to fit in this in the end somehow. The mind is not my area. That's the difficult part of philosophy. I'd like to stay out of the difficult areas. But there's one thing maybe that could be, and I think is actually used, and still both, I think, in philosophy and in physics, and it's the role that experience plays in deciding when to accept and reject a theory. And the idea comes from McTaggart, notably that experience does at least provide one form of indubitable knowledge, notably knowledge of our inner states. So if I'm seeing an apple on the table and it appears to me as red, I know that I'm having that experience. I just don't know whether there is an apple there, right? But I know the experience that I'm having. So my experience does not give any evidence as to what the world is like. But any idea about the world that fails to explain why I can have this experience is somehow inadequate, right? We have to refine our views about reality until we can explain how it is that we can have this experience that we have, because indubitably we do have it. Yeah? And it seems to me that in the philosophy of time, for instance, that's one of the deciding factors. If a theory of time is unable to explain how we can still have experiences of passage or these ideas, I mean, it doesn't matter, we don't have to explain that time has those features. We just have to explain how the time that doesn't have it can still give rise to the experience. And I think some of the worries with the appearance of reality in a way are closely related to this. Somehow we have to link it up with how we experience the world, even though our experience does not give any evidence at all about how the world is. Yeah. But it becomes like a criteria for success for a theory. So yeah, so let the final words be just don't forget about the mind and its content in the project of unifying our view of the world. Thank you.
I am Jouko Hämmäläinen from Tampere. I have to work with two spaces. It's the cosmological space and the bigger space in my head. How are your thoughts and experience with possible limitations of limitation of knowledge in human mind?
I accept that we have limitations, and as Wang, I think it was said that we might be facing really an eternal quest for knowledge, never arriving at the end. Yeah, hoping all the while that we're coming closer to something. Yeah, but as with regards to other aspects, I'm not sure. I'm still struggling with the mind. Yeah, and not just my own. You know, that's we all do that.
Okay, thank you. Now we'll have to move on. Thank you, Valdi.
Yes, thank you.
Next speaker is Professor Lawrence Gold from Hartford University.
You better say University of Hartford, otherwise it sounds like Harvard University.
The topic is quantum ontology of De Broglie and Bohm with reflections on the meaning of probability.
At some point in the presentation, I'm going to have to jump out of the presentation to show you a little video and then jump back into the presentation, but it'll be pretty quick. At least that's the way it was in practice. Actually, why don't I start with the video, and it doesn't have to be from the middle. I'm going to talk, as you heard from the title, in part of De Broglie, and De Broglie's idea was to connect the wave with the particle view, and I'll just show you briefly a little animation of that. You'll notice that there's a green wave that's traveling from left to right. There's also a particle that's indicated by this up and down visible line that's traveling from left to right. They're traveling at different speeds, you see, because this peak over here just passed the particle, okay? But this thing to notice is that the particle is such that it peaks. It coincides with the peak at certain instances. And this was a problem that De Broglie was trying to figure out the solution of how can you have a wave associated with a particle. I'll say a little bit more about that in the presentation. So now I'll get out of the animation and get into the presentation. Okay, so this is the title, repeated. I'm Gould, the University of Hartford, and here are the topics of the lecture. I'm actually very happy that Valdi has preceded me because now I can understand even better the ideas of metaphysics. And I'm going to talk a little bit about it. So I want to discuss first what is the philosophical starting points, and then something that pertains to the physics, in particular, how conservation laws are tied in some way to the interpretation, Bohm-de Broglie interpretation of quantum mechanics I'm going to discuss. There's a qualitative aspect and then there's a quantitative aspect, basically meaning the mathematics. And then I'll bring in the de Broglie idea in quantum theory and mention its connection to ontology, and then I'll summarize. Yeah. So very brief philosophical considerations. Valdi had done a very nice job, I think, dealing with the metaphysics. And he did mention that metaphysics is a study of being as such, which I think is the way Aristotle talked about metaphysics. By the way, metaphysics is not the term that Aristotle coined. It refers to one of the books of Aristotle's corpus, and it came after the physics. He has a volume on physics. Now, metaphysics is being as such, and then epistemology has to do with theory of knowledge. How do you come to know, etc. So on my website, I had this statement, which I just was able to use twice so far, yesterday and today. Philosophy, everybody has one, implicitly or explicitly. So the only issue is whether it controls you or you control it. There's a lot of writing over here. That's for the people who like to do reading, but I'll hit the main points. There are a number of physicists who have explicit philosophy. One is Albert Einstein, he said he believed in the external world as necessary for the doing of physics and also in causation. Max Planck believed in causation, but he thought that you have to have a way of following all of this, of what's going on. So he has this belief in an ideal and omniscient spirit. Okay, I don't have that belief, but he does. Okay, Ernst Mach had the belief, he was a good physicist, but he was influenced by Immanuel Kant. So he took the point, although it's puzzling with some other points he took, that we can only know our appearances. Okay, so you basically, if you're trapped inside your mind. And for Kant, Kant said you can't know the thing in itself. If you really want to know it, though, you have to know the thing in itself. But you can't know it because you have to interact with it, okay? And the assumption is that knowledge of the thing can only be done in a kind of what's called a diaphanous way. That is, you have to somehow contact the thing in itself. But there's been arguments that that's not the way knowledge proceeds, okay? And Kant is an idealist, okay? Even though he tried in the second critique to justify the existence of an external world. Generally, there are different views in epistemology and metaphysics. Hume, for example, thought that you couldn't really find necessity in causal reactions, because his view was that our knowledge is, our concepts are based on contact with the sensory world. And if you see one billiard ball hitting another billiard ball, there isn't a sensory indication of this, like a flag waving saying necessity or a bugle going off about necessity. Locke had a view that perception is not direct, so the mind builds up out of different pieces of information from the object, and that's how we get the view of the object as a whole. That's not the only view, okay, that exists in philosophy. Then there are others, Berkeley, Descartes, Mach, I mentioned, and these others, okay. They all have some views in philosophy. The connection between metaphysics and epistemology. Usually, from what I've seen, one tries to reason to, or try to reason to, an external world. I think the more reasonable approach is to think of philosophical axioms. That is, these are principles such that one must use them in any attempt to deny them. Examples from metaphysics. There is an external world independent of one's consciousness. Now, that's not something that one tries to prove. That's something that if you attempt to disprove it, you have to use it. That's the claim, okay? And this is a difference from Einstein's belief in such a world. He believed in the external world, but I haven't seen arguments from him about its philosophical axiom. One of the parts of metaphysics is that the law of identity, okay? And it's axiomatic because you have to use it in any attempt to deny it. You could try it out if you don't believe me. In epistemology, there's another axiomatic aspect. And in this respect, Descartes was right. That is, you can't claim that you're not conscious because you have to use consciousness in order to do it. Okay? And the law of non-contradictory is, along with the law of identity, I think axiomatic in this sense. I think all philosophy, all science relies on non-contradiction and the law of identity, explicitly or not. Okay? There's an extensive discussion of some of the main courses in philosophy, and also about direct perception, which draws on the works of J.J. Gibson from Cornell University. And that can be found in a book that I don't think is that well known. It's called The Evidence of the Senses by David Kelly. It's a Louisiana State Press, I think. And there's a very nice review giving the topics and page numbers by a philosopher by the name of Stephen Hicks. Okay. Okay, let's talk a little bit about the physical aspects, the structure of conservation laws. You see things, and some of them never appear to disappear from the world. They just might change their form, like Proteus. So, for example, if you imagine water over here, see, there's water. Let's see if I can... yeah, okay. So here's a blob of water now, and then later on has a different shape, and then it has later on still a different shape. Still water, it still hasn't disappeared, okay? But is it true that it can't disappear? And the answer is no. For example, in chemistry, you can break water up into hydrogen and oxygen, right? How about tennis balls? You can burn them, okay? You can't play with them anymore. How about euros? Okay, so maybe illegal, but you can burn euros too. How about energy? Can that disappear? Well, as far as I know about physics, the answer is that energy cannot disappear, it just changes its form. Okay? It goes, for example, from potential to kinetic if you drop a ball. Okay, okay. Now I want to connect to some of the main laws in physics. The conservation laws, what people usually hear of. There's something that's preceding the conservation laws called a law of continuity, and then more abstract is the balance law. I'll give you a brief idea of these ideas. So, for example, let's say you have a physical property and it's quantified. So the volume, for example, 5 cubic meters of water. You have an inside region and you have outside regions. For an example of a conservation law is you can have 3 cubic meters of water near the right side, 2 cubic meters of water near the left side of the inside region, okay, at one time. And another time you have 5 cubic meters of water, could be near the center. Well, you still have 5 at the beginning as you have later on. They're just differently distributed. That's an example of a conservation law. But the total amount, you see, doesn't change. Now, a law of continuity would be how much of the quantity leaves, whatever leaves goes from the inside to the outside. For example, let's say 3 cubic meters of water disappears from inside during some time interval, then 3 cubic meters of water must flow through the surface to the outside. That would be an example of a continuity equation, okay? And the balance law is that if you have some cubic meters that is leaving, for example, if you have 5 cubic meters of water remains on the inside, while 3 cubic meters of water flows to the outside, then 3 cubic meters of water must flow into the inside from some source, okay? Because you have more flowing, and this is called the balance law because you have a source from outside the region. Okay? Now, the field of physics appears to be dominated by deterministic causal theories. That means if you have well-posed initial conditions, then the development of the system is specifiable at a later time. So the values of an appropriate set of variables specified at one instant through some region of space, along with the system's fundamental equations, then can, in principle, enable you to predict the value of those variables at any other later time in that region. And examples of this would be Newtonian mechanics, special relativity, general relativity, electromagnetic theory, and even classical thermodynamics. So now we get to de Broglie. I think it's actually pronounced de Broglie, but in the United States, no one knows what you're talking about if you say that. So I say de Broglie, okay? And Einstein looked at the classical electromagnetic radiation that was predicted by Maxwell as waves, but then he had arguments why they could be thought of as particles. And he had a paper in 1905. 1905 is the Annus Mirabilis. It's the year of marvels because he had the special relativity paper as well as this paper as well as E equals mc squared all in the same year. Okay? De Broglie said, well, if Einstein could go from wave to particle, maybe particles have a wave aspect. I showed you something of that in a little video earlier, okay? And what people usually don't know about this wave-particle development of de Broglie, okay, is that special relativity was essential in arriving at his conclusion. That is, the particle being at the peaks of the waves that I showed you earlier, that was a puzzle, okay? And special relativity was necessary in order to solve it, okay? And I showed you the animation, we'll so skip that. Okay, now let's go to the double slit experiment. If you took light, people knew since around 1802, Thomas Young's experiment, thinking of water, you can think of water waves going through 2 slits, and you get on the screen over here, you get a pattern where there's, if we think of light now, where it's very bright over here, then it's dark over here, it's a little bright over here, and a little bright over there. What's remarkable is that if there's a wave nature associated with particles, then you can speculate there might be such an interference, it's called an interference pattern over here, and there is, okay? So if you do it with electrons, you get the same kind of pattern, okay? And here's an example from a paper in American Journal of Physics of an actual experiment that shows you the buildup of the interference pattern, okay? Over here, there's 11 electrons. You could hardly see them. Then 200, then 6,000, and you start to see areas where there's brightness and areas where there's darkness. Then 40,000, and then 140,000. Now you can pretty clearly see the interference pattern. Each of the dots of light is where an electron struck the screen. This was done by Tanamura in Japan. And so between the slits and the screen, one can ask the question, where is the particle? How fast is it going, and in what direction is it traveling? Okay. Now the usual answer is what's part of the Copenhagen interpretation, and adherents to that school would be Heisenberg, Bohr, Schrödinger and Einstein on the opposite side of the issue. The usual answer can be given figuratively as a great smoky dragon, and here's the way it works. The electron is the dragon's represents the dragon's tail, and where the that going through a slit, and where the electron hits the screen is where the dragon bites the detector. In between, smoke, okay? We don't know what's going on, and we can't know, according to the Copenhagen interpretation, what's going on. Okay, I'll skip the details over here. What Feynman said, characterizing electrons and photons, the behavior, he says they behave in the same way. Quote, they are both screwy. Now, I think the Finnish word is, I left out the dots, but I think it's taratanuta. I don't know how you spell it. Is that correct? Yeah? Okay, I see some shaking of heads, so I must be on the right track, okay. Okay, now in terms of the mathematics, I'm going to be really brief on the math. What you have is non-relativistic quantum theory, and what I'm showing you over here is what's called the Schrödinger equation. That's the dynamical equation. That's the equation of motion, and it's the equation of motion of the wave, but remember the wave is associated with the particle, so you can connect the two. This term over here represents the kinetic energy. This is a Laplacian for the people who are in the know here. This term represents the total energy. This funny symbol over here with a 4 subscript represents the partial derivative with respect to time. Phi is the wave function, okay? And then U is a potential energy, okay? So you have a kinetic energy, you have a potential energy, and you have a total energy. And that's basically a conservation of energy equation. And then what you do, you take a classical conservation of energy, and the ansatz is you replace the usual classical symbols by operators, differentiating. Okay, M is a particle's mass. Okay, moving on. The Bohm ontological interpretation is, well, you can't say what's between the slits and the screen. Okay, so you start with a wave function. We're calling it phi here, and then it can be written this way. This is an exponential. The I is the square root of -1. S over here is called the phase constant, or the phase function, and H with a cross means Planck's constant divided by 2 pi. Okay? I'll show you what the arrows mean in a moment. Okay? If you put the wave function into the Schrödinger equation that I showed you earlier, the mathematics gives you 2 main equations. One of them is interpretable as an energy conservation. It's actually technically called the Hamilton-Jacobi equation. This grad S thing over here, that represents the momentum. So if you have a momentum squared over 2m, that's classically what's thought of as kinetic energy. And this would be representing total energy. This is the classical potential energy. So what you have then, that represents total energy. This represents the kinetic energy. And the classical potential energy is this. What's this other term? Okay. Q. That's called the quantum potential, or it's the potential energy that comes out of the quantum treatment, putting this into the Schrödinger equation, I say the wave function, the Schrödinger equation, okay? Now you get this thing over here, you see this del square term over here, and that has a big effect on where the electrons land. The ontology is that there are things between the slits in the screen. It's not all smoke of the smoky dragon, okay? The other main equation, besides the energy conservation equation that comes out of this, is the probability continuity equation. Now, if you remember back, I showed you that continuity means that what leaves one region flows into, what leaves the inside flows into the outside, for example. That would be continuity. The thing that's flowing over here is supposedly probability, but I have some comments about probability. The standard interpretation is probability flow, okay? So what does it look like pictorially? Well, the quantum potential looks like this, okay? So where you see here, that's at slit A. So the slit A and slit B are in the screen behind. In the front is the screen, okay? And the quantum potential at the screen looks like this, and in between it has this structure. Now, the thing to notice is that the valleys get steeper as you get closer to the screen, okay? And the quantum potential gets smaller, okay? Now, something getting smaller as you get further away from it, that sort of makes sense, right? Because if you get it further away from the source of light, it's dimmer, and further away from a source of sound, it's fainter, okay? But what happens with the quantum potential is that it gets steeper as it's closer to the screen, farther from the source. And it's the steepness that's causing the electrons to clump in certain areas and not in other areas, okay? Now, there's a suggestive picture that I could show which indicates the aspect of a three-dimensional picture that if you move it further away from you, the mountain peaks that appear in the picture get larger, okay, instead of smaller, okay? But you won't be able to tell it from the picture that I show you. Here's the picture, okay? It's one of these things where you have to relax your eyes and sort of look at the center, and what will happen then is in the center there will be a mountain peak, and then there will be a first circular valley around that, and a second circular valley around that one. If you can see it, you're a better person than I am in that respect. I have to stare at it for quite a while in order to see it, okay? So that's supposed to be indicating that as you get further from the source, something gets larger. In this case, it's the mountain peak. Okay. So what do the trajectories look like if you say that you can describe where the particles are in between the slits in the screen? They look like this, okay? And here are the two slits back here. Here's the screen, you see. And you have major clumping over here, then not over here, and then more electrons over here. There's something over here that people usually don't mention when they talk about the trajectories. It's a different prediction that's made by quantum mechanics, although I don't know of anyone who's able to verify it. The prediction, according to this, the quantum potential idea, is that the trajectories coming from this slit never cross over into this region, and the trajectories coming from this slit never cross over into this region. I don't know how to actually determine that. It's probably an uncertainty principle working against determining it, okay? So do you have now a deterministic causal theory? Well, Bohm considers the wave function in a state of random fluctuation, some of this later work. And so each trajectory would be shown due to the average motion. How much time do I have? I think I'm close to the... Almost, okay, so I'm almost finished, actually. What he says is that it's possible that you could have tiny fluctuations by non-determinable aspects in the medium between the slits and the screen. And I put in at least so far, because if you believe in causality, it's a metaphysical principle, then the advice is keep looking. And that's what physicists usually do. If they can't understand something, they just keep looking. So as Bohm mentions, his interpretation, while being causal, is not strictly deterministic, okay? I would argue as much for free will, but that's another argument, okay? So finally, the wave function is a measure of probability. Conservation of energy is a principle of physics that has causality built in. So if you find you're missing some energy in some region, then you're supposed to look in other regions to find the missing energy. The energy books have to be balanced, okay? And probability, as I view it, and so there are other people who view it this way, is a measure of one's lack of knowledge, okay? If you don't take it as a measure of a lack of knowledge, you could say, well, there's a smoke in between the slits in the screen. We can't know, and we'll never know, okay? Give up, okay? So probability then operates under certain constraints. If you flip a coin, you say, what's the probability of getting a heads? The probability of getting a heads or tails is 1/2. Usually, but you have to remember what your constraints are. I have mentioned, and it's true, that I flipped the coin once, and it bounced about a little, and then it landed on its edge, okay? Now, it landed on its edge because the constraints were, it's bounced about, it hit the side of the refrigerator or whatever, and that happened, okay? So there are always constraints that come in when one talks about probability, whether it's Bose-Einstein statistics, Fermi-Dirac statistics, okay? So in terms of the Bohm-de Broglie picture about probabilities, I don't think probability propagates. The probability is a lack of our knowledge. The matter wave propagates, and it is frequently referred to, the psi function or the wave function is also frequently referred to as the matter wave. That is some kind of stuff, okay? So in summary, we had some philosophical starting points that related to the later discussion, structure of conservation laws, and qualitative and quantitative that connected to the equation of continuity that comes out of the Bohm-de Broglie theory. Then we talked a little bit about quantum theory and ontology, and finally ended with causality and probability, and that's where I'll end there. Thank you.
All right, welcome back. And the next speaker is Professor Tapio Ala-Nissilä from Aalto and Loughborough Universities. And the topic is quantum mechanics in action.
Yeah, thank you. Nice to see so many people here today. We already had 2 days of workshop where we were discussing these topics in more detail. This talk will be a bit more elementary than what I would usually give for a professional audience. So my field of expertise is not cosmology or astronomy or relativity, but it's statistical mechanics, quantum mechanics, and we're actually working on these devices. So I will also, besides telling you some new things about quantum mechanics and maybe trying to unravel some of the mysteries or some of the things that people think as mysteries in quantum mechanics, I'll also try to tell you about some new things that we can do in quantum mechanics in action by building devices that use quantum mechanics explicitly. And I'll try to be as precise as I can to define what I'm talking about. So this is the plan. I will not go to any of these issues in depth because we have the panel discussion, and then you can ask about the details if you want and discuss these issues a bit more. So my point really is that I want to make it clear that I think there's a lot of mystery associated with quantum mechanics, and most of it is this confusion or mystery, or I would say the mystery is because of confusion. It is sometimes difficult to explain these things that happen in quantum mechanics in layman's terms, and I'm not sure I can do any better than anybody else, but at least I'll try to explain why I think many of these things that are called mysteries are not really mysteries at all. Let me just make a brief remark. There was no time for remarks. So as I said, I'm not an astronomist, but I know that last year an extremely precise and sophisticated measurement of the expansion of the solar system was made by the Americans, by NASA. You can look at the paper if you wish. So this is from last year. And the correct number is 1.5 centimeters per year. And this is completely due to the loss of the mass of sun due to its radiation. So actually this experiment shows that there is no expansion of the solar system. But we can discuss this in the panel session. Okay, let me go to my main topic. This is my definition of quantum mechanics. I'm sure most of you are not physicists, but basically the simplest way to define quantum mechanics is that if you go to small enough things or high enough energies, you will have to modify the laws of physics. And this is an experimental fact. And this was, of course, a big surprise. I guess in the late 19th century, many people believed, and physicists believed, that the mechanical picture of the world, the mechanistic picture of the world and reality is complete. But then there were phenomena that could not be explained, which came about with sophisticated techniques, new experiments, and these needed to be explained. And that's how quantum mechanics came about. So physics is an empirical science at heart, right? Like Richmond Feynman says, it doesn't matter how smart you are, it doesn't matter how beautiful your theory is, if it doesn't agree with the experiments, it's wrong. Okay? And this is what quantum mechanics is about. It agrees with the experiments. These are the famous people. The last one on the right-hand side is Paul Dirac. This is one of the few equations I'm going to show because it's called the Dirac equation. It's a relativistic equation for quantum mechanics. And it is one of the most beautiful results in the physics of the 20th century because he actually derived this result by just based on symmetry and conservation laws, exactly what Larry was talking about. So he showed that at least in this, for many systems, symmetry and conservation laws actually precisely determine how the physical systems behave, and it can be put in a mathematical form. Okay? Now, this is called the first quantum revolution because, of course, once we understood the existence of atoms and electrons, we could build devices based on them, and that's what we have today. Now, there's a difference in technology that's being now conceived, and I will talk about that in a minute, but let me just say that why this is called the first quantum revolution is that these devices that we have they're fundamentally quantum mechanical, like the transistors and diodes and things like that that make up computers. But actually they don't really use quantum mechanics directly. The essential features of quantum mechanics are not used in these devices directly, or these devices don't exploit quantum mechanical features explicitly. Another way of putting that is that these devices can be often modeled with some simple classical equations. So, like if you look at the flow of a current in a circuit, the electrons are quantum mechanical, but the current can be described by a simple macroscopic current. You can write very simple equations without any quantum mechanics and explain how the current flows from one place to another, right? So in that sense, these devices are not exploiting quantum mechanics. So what I'm going to explain at the end is that now we are building devices that actually specifically exploit quantum mechanics. Then I have to define what is quantum mechanics, so let's define that more precisely. So what is it that makes up quantum mechanics? I mean, if I make a poll here, if I had time, I would come and ask, well, what do you think is quantum? I mean, what are the signatures of quantum mechanics? What is it? When is something quantum and when is something not quantum? Now, there's several things that have been defined to be quantum. There are a couple of them here. There are many more. The most well-known ones are the interference effects. So this is what Larry was talking about. So you will get this pattern from two slits, whether you shoot light or electrons or any other objects, quantum mechanical objects through these slits, they will make a wave pattern. So there's this particle-wave duality. That's one of the things that initiated quantum mechanics. This needed to be explained. So that's called interference. Actually, all waves interfere. You can see this on a lake. If you make waves in two different places and they meet, you can see that they can either cancel out or enhance each other. Okay? The second one is called wave function collapse. That's a bit more technical, but the point is that in this picture, the particle is not, if I have a particle that's described by this wave function, a quantum mechanical object, it's not in one place at any given time, but it's sort of spread out. Its wave function is spread out. But if you measure it, if you make a measurement, you can precisely pinpoint where the particle is after the measurement. And this is called the wave function collapse. So in the wave function picture, that means that the particle position collapses to a well-defined point in space. And that's the answer that you will get from the measurement. So these are the two typical signatures of quantum mechanics for single particles. But it turns out, in fact, and this is really interesting because this was shown last year. Okay, so we're not talking about 1930s, we're talking about last year. Okay? That in fact, if you take just a single quantum particle, just one particle, okay, that is quantum, or one quantum system with d levels, all its quantum mechanical, what we call quantum mechanical properties, can be classically simulated. That's what this picture is about. It's a technical thing, so I will not go into the details, but one can construct what is called an interference circuit that is completely classical, that gives you the same results as if you were to measure quantum mechanical particles, single particles. So one can actually say that single particles do not exhibit any quantum mechanical phenomena, in the sense that all the things that we think as quantum mechanical for single particles can be simulated by classical but stochastic, probabilistic methods. Okay? So the real definition of quantum is something that cannot be simulated by classical, stochastic, or probabilistic methods. And for that, you need more than one particle. And for that, you need entanglement. I know this word entanglement also is very confusing because this is used from anything to, from insects to humans to whatever. It has a precise meaning in quantum mechanics, but you can think of entanglement as the word says. It is combining two things into something that's more or different from its parts. Okay, as you can see somehow in this picture. So when you combine two or more quantum systems, and if they entangle, that means that they become a new whole. Okay. That is different from having two separate quantum systems. And now the point is that if you separate these two systems, when they have been entangled, they will not go back to the old parts, unless you do something to them, okay? They are so-called correlated. So in the professionals, we use the word correlation, okay? So there is quantum correlation between these two parts of the system once they have been entangled. Before that, not. But if you entangle them, and then you separate them, they are no longer the same individuals that they used to be, but they are actually a combination of half of the combination. And in this way, it's really easy to understand the spooky action at the distance, right? So what is that? So this is the thing that prompted Einstein in 1935 to say that quantum mechanics is incomplete, which is a polite way of saying it's wrong. And this was headline news. This was still at the time when scientists were quoted in the headlines of newspapers. Today you don't see that anymore. Not even in the Helsinki Sanomat science section, you don't usually see a lot of science that's quoted. But this was big news. See, he concluded that this is impossible. So if this happens, this is predicted by quantum mechanics, but it doesn't make sense. So if it happens, then quantum mechanics must be wrong. So the key is in this entanglement again, like I just said. again, if you take two quantum systems, spin up and spin down, once you combine them, they are no longer a combination of spin up and down, but something different. And when you separate them, and don't perturb them, just leave them alone, the separated parts are not spin up and down. It's a combination of the spin up and down. There's a quantum correlation, right? I mean, it's like if you mix two fluids and you put half of the fluid in another jar, that's not going to be the, say, yellow and black. It's not going to be the yellow or the black. It's going to be a mixture of the yellow and the black. In the same way, once you have entangled these systems and you separate them, they're no longer the same as they used to be, unless you do something to them. And then you decide what values they take. And so this is the famous non-locality measurement. I should say that this word, again, non-locality is confusing. There's nothing non-local in quantum mechanics. This non-locality refers to the fact that if you try to explain this classically, you have to introduce the idea of non-locality, spooky action at the distance, which is impossible, or at least doesn't make any sense. But in quantum mechanics, this is completely natural. There's no mystery. Like I said, once you mix these things, they're not going to be the same as before, except when you force them to be one or the other, right? So this experiment has now been repeated many times. I'm showing this one here from, I think this is 3 years ago. Simply because this is where they made absolutely sure that there was nothing that could spoil the experiment. This experiment sounds simple, but it's actually very delicate because quantum systems are so delicate. So they actually did an extremely careful plan of the experiment so that what they measured would not be affected by anything that they could not control. So what is the idea here? They have this entangled systems spins, in this case, in this central building, and then they separate them very carefully, not to perturb them, to keep this correlation, and then they send the two parts in two different places. And then they make a measurement on one place. And that immediately determines the value of the spin in the other place. And that proves this feature of quantum mechanics. Last year, the Chinese and the Austrians did another experiment repeating this with satellites. So the distance they measured, they made this measurement between Peking and Vienna, where the distance is thousands of kilometers. So there's no way that information could be passed between these two places by any means. So this really proved, well, this experiment already proved, and earlier experiments, that quantum mechanics has this feature of quantum. I would not use the word non-locality. That's not a good word. I would use this persistent quantum correlation. So if you think about it, there's really nothing mystical about this. It's just correlation. Something that we don't see in everyday life, but we don't live in the quantum world. Okay, now let me speculate, since there have been a lot of speculative talks here today. So everything I said so far is a scientific fact, based on experiments, okay? As physics should be. But there are a couple of interesting proposals recently. I just want to mention to inside your imaginations, this is complete speculation. But again, it's based on experiments, in part. It's based on theory, but experiments mostly. So there is a proposal or an experiment done 3 years ago, 4 years ago, 5 years ago, that actually the origin of time is due to quantum entanglement. So they made a very simple measurement of an entangled quantum system and showed that unless you entangle yourself with this quantum system, then there's no dynamics, there's no evolution of time. So it doesn't prove anything really, but it does suggest that it's possible that time is not an absolute coordinate, but it's an emergent quantity from quantum mechanics. So fundamentally, the time in the universe could be due to quantum mechanics and not an independent variable. Again, this is pure speculation, not a proof, but an interesting idea. Physicists are always open to new ideas. there's even a higher level of entanglement. And this is actually based on mathematics. It has been shown in several cases that if you have something technical called a conformal field theory on a d-1 dimensional surface, like a 2D surface, then you can reduce that theory to a general theory of relativity in the higher dimensional space, in the so-called bulk, in the d-dimensional space. That's a really interesting idea, because this would say that also the force of gravity is not a fundamental force of nature, but it also emerges from quantum mechanics. Maybe, maybe not. We certainly know that the other forces are fundamental, but it's possible that gravity is not a fundamental force. For the other forces, we found the mediator particles. We know how they work. We understand these forces. But for gravity, we don't. We only have the classical theory of gravity. Okay, so again, speculation. Don't take my word for it, but it's an interesting idea. Okay, I have 10 more minutes, so let me discuss what I mean by the second quantum revolution and why we talk about this issue so much. So let me repeat. Most of the current technology we have is not based on exploiting quantumness. And now you should know, next time when somebody asks you, well, what is quantumness? It's entanglement, okay? So we don't exploit entanglement or superposition in many cases. Laser is really a purely quantum mechanical device, and it utilizes coherence of light. But I think also for laser, if you just are interested in the output and the operation, you can sort of write semi-classical equations. So in some sense, it's not exactly quantum device in the same way as I will explain next. So the idea is that in these new devices, we explicitly use entanglement, so the real quantumness. In fact, superposition is related to entanglement, but let me just talk about entanglement for simplicity. Okay, so the building block, the simplest building block of these new devices or this new quantum technology is something called a qubit. And you can actually see what it looks like. I mean, these are now routinely made, even here at Aalto, in Micronova, we make this routinely for the experiments and for the devices that we do. Well, not me, I'm a theorist, but my experimental colleagues. So the qubit is a two-level system, but it's a quantum mechanical two-level system, so it can assume any state. It can be in any superposition of these 0 and 1 states. So it doesn't just have two values, but it can have any value in between. And then when you make a measurement, then it collapses to 0 or 1, okay? So it's like a spin. You can think of it like a spin, mathematically. So the computers we have specifically are not quantum mechanical at all, because in fact, we can all make a computer here, okay? So if I tell you that 1 means hand up, 0 means hand down, we can actually make a computer with each of you acting as a bit in the computer, and we can do a calculation. Okay? So for a digital computer, a binary computer, you don't need any electronics. You can do it with anything you want, even with humans. I think the Chinese population would make a powerful computer, but of course that would be somewhat difficult to control. So, but in principle, you can do this with your friends. You can make a small computer and do some calculations. If you don't believe me, it's not difficult. But of course, in practice, our computers are electronic because it's fast and cheap and small. But a quantum computer is something completely different. So it really is something completely different, because the basic building blocks are not bits, but they are qubits. And that means that so every bit in a standard computer can have two values, yes or no, right? So you can store one bit of information. Either there is something or there's nothing there. However, in principle, since a qubit can be in a superposition of any of the two states, you can store a huge amount, almost infinite, theoretically, into a single qubit. And then you connect these qubits, so you entangle the qubits. Remember, for entanglement, you need more than one quantum system. So one qubit can be in superposition of its own states, but then you can entangle multiple qubits. And then you get the real quantum effects, okay? Real quantumness, like I said. And then you do quantum operations, and at the end you collapse these qubits and you read the answer. So the advantage is twofold. With just a relatively small number of qubits, you can store a huge amount of, you can handle a huge amount of information, and then because all these operations happen simultaneously, you can do like kind of parallel computing at the same time. So you can search for all the possible options at the same time. And that's why this would completely revolutionize computation, and you could decrypt all the highly encrypted passwords and all kinds of things. So we have these already. So the D-Wave has been in market for, I think, about 10 years or so, maybe a bit more. They claim to have a quantum computer, but actually it's not really. It's a very limited machine. It has qubits, but it doesn't use entanglement directly. It doesn't fully utilize the quantumness of the qubits. And so that's why, to be precise, you shouldn't really call it a quantum computer, but a quantum annealer. Okay, we can discuss after my talk what that means, but you can only apply it to very specific problems. If you have what is called a universal quantum computer, then you can do almost anything with it. So IBM, Google, Intel, all the big companies, Microsoft, are getting into this now. And IBM has just released this year, so this is from this year, a 20-qubit universal quantum computer. So this guy is not commercially available. It is a test machine, and it's not completely reliable, but they are really trying to build what is called a universal quantum computer that fully utilizes the entanglement and superposition and the entanglement between the qubits, so that you could actually do all these exciting things that we think we can do with the quantum computers. They are putting, as you probably know, hundreds of millions of euros or dollars, doesn't matter, into these. I think Google is spending $1 billion in this project right now. Google is actually trying to build a 72-qubit quantum computer. They have bought complete research groups from universities to work on this, because it really is still science. It's not engineering, not completely. And at Aalto, we're also building a small one just to see how it works. Okay, the last thing I want to talk about, so my research relates to the quantum computers, but also something called quantum thermodynamics. So let me spend the last couple of minutes discussing what does quantum thermodynamics mean? I mean, of course, you can put the word quantum in anything you want, but it doesn't mean anything if you talk about quantum consciousness or, I don't know. I mean, it doesn't. So what does it mean if I talk about quantum thermodynamics? Well, actually, it's a well-defined field of research. I think everybody knows thermodynamics. We all look at the temperature maybe multiple times a day. That's what thermodynamics is about. It's about temperatures and engines and heat and work. And of course, this really gave us the Industrial Revolution, with the mechanical engines. It is fully macroscopic theory. So this was developed well before any microscopic theories, and it's a beautiful mathematical theory, actually. But it has no quantum mechanics, no microscopics in it. But it's been extremely successful. So the question is, if we go into really small systems, these quantum systems, can we try to understand them somehow in a similar way? And at first it looks like there's a contradiction, because thermodynamics is the theory of macroscopic systems, and quantum systems are microscopic. So can you even try to describe these microscopic systems with something similar to thermodynamics? And that's an interesting topic. The reason that this is important is that we can actually build these devices. So this is a device built last year by my colleague Jukka Pekola at Aalto. It is a quantum heat, what they call a quantum heat engine. So there is heat flowing between the red and the blue circles, and the red and the blue circles just indicate temperatures, but there's a qubit in there, in the center of each circle. So these qubits are at different temperatures, and then there's heat flowing, and there's a way to control the heat flow. You can see the valve in between. There's a way to control the heat flow between these two qubits. So this thing works like a mini engine, okay? Quantum mechanical engine. It's a real quantum mechanical engine. The question is, because of laws of quantum mechanics, its behavior is different from the classical engines. And in order to understand how this works, we need to understand how does the heat flow in this quantum world, what is the energy of the system, what is the work, what is the entropy, all these things that we need for thermodynamics, and that's what we've been working on. It's a really interesting topic because it's not so trivial to try to understand these concepts for microscopic systems. But let's say we want to say, how efficient is this machine? Is this machine somehow more efficient than any classical machine? To answer that, we have to know the power output of that machine. So we need to know how much heat is generated, how much work is put into the machine, or how much work does the machine do. You see, we need these thermodynamic quantities. So that's an interesting research topic, ongoing. Okay, so I think I'm right on time. Thank you for your attention.
So we got time for one question, in fact, before the panel, before the next presentation. If somebody has a direct question for Tapio, you can present it now. Wait.
Thank you for the presentation. I have a question related to your last topic about quantum thermodynamics. Is it possible to mix actually thermal radiation and quantum mechanics, or not?
Well, so it depends what you mean by thermal radiation, right? So there is a quantum theory of radiation that we can use as part of the system description. So yes, it is possible to do that, but then you have to do that quantum mechanically. You can't use classical theory for that. So that is the challenge, really, that in this regime we have to use quantum mechanics to try to define these quantities. So everything has to be quantum mechanical. Yeah.
All right, then we'll move on to the last presentation. And then we'll have a panel discussion. So, last speaker is Tarja Kallio-Tamminen. Her presentation's title is Dynamic Universe, Natural Science and Philosophy in Unison.
Now it is time to take a more general approach, somehow to understand in what kind of reality we are living. So conception of reality, worldview, it provides window into reality. And it is very important for people to navigate in their daily life. We need to understand in what kind of reality we are living, how to explain things in a suitable way and act in a sensible manner. And this kind of basic ideas about reality, they are very long-lasting cultural constructions which are based on metaphysical presuppositions, and they are taken as self-evident in normal times. And they are only recognized as temporary constructions when they are failing to explain new facts. We have been living in the Newtonian world framework that was created in the beginning of modern era, and it was thought as the real world that was described by the Newtonian physics. In that framework, natural science and philosophy, they were in unison. It means that there is metaphysics as well as physics. They come together in a coherent conception of reality. Because science as such, it is blind without philosophy. There should be a proper interplay between science and philosophy, a balance between empiricism and rationalism. And then some idea how I understand natural philosophy. I think it is the primary thought focusing on existential things. It includes metaphysics, ontology, epistemology. And philosophers in this field, they have tried to move from phenomena to factual, from transformation to some eternal laws which stays forever, from perception to pure understanding. And this kind of philosophizing, it bloomed in ancient times and at the turn of the modern era. And once again, when the present worldview based on Newtonian physics has been realized to not correspond with reality, we are in a phase when natural physics philosophy is once again needed. In this kind of new conception of reality, we should better understand the nature of reality, better than what the abstract theories of modern physics as such are able to provide us. Abstract theories, they are intangible for general public. Nobody anymore knows in what kind of reality we really live in, how these modern theories should be understood and interpreted. And that's why, because I had been studying the interpretations of quantum physics, and I realized there are plenty of them, and it is impossible to choose, make a choice between them, because there are no empirical tests just to find out which would be the right one. And that's why I very much got interest in this dynamic universe model theory when I heard about it 20 years ago, because it provides a new kind of structure and dynamics for physical reality. It unifies the domains of theory of relativity, quantum physics, cosmology. It gives a kind of general framework in which we can understand reality in a new way. And this is a very good theory as far as I can understand. It exceeds the level of present theories in theoretical virtues, which has been provided by philosophy of science. There are criteria, as Avril told us in the morning. So it is a more encompassing theory based on smaller number of premises. And what is most important for me, it provides a clear picture of reality where Newtonian clockwork turns into an all-embracing entity that organizes itself into a multi-layered, unbroken whole. It settles several age-long disputes in natural philosophy. What is the basic substance of being, origin of movement, nature of mass, energy, entropy, and the relations between these concepts. And also important thing, as Valdi told in the beginning or already, a proper theory of reality, it should also provide a place for mental phenomena And this is what I think is possible to do in the context of dynamic universe. And in this talk, I'm going to go into more details into this issue I just gave in a nutshell. We will trace how reality has been understood since antiquity to present day. And in antiquity, basic approaches to reality, they were already given, defined, and ancient thinkers, by no means they were inferior to us. We may have more facts, but it is by no means easy to understand deeper reality which these facts indicate. And these pre-Socratic philosophers, they started trying to find out the basic substance of being, and then mathematics was somehow taken to also provide a kind of basic understanding into reality. Then logic was used, and Heraclitus understood that in addition to being, becoming also needs an explanation. And there was a lively discussion during several centuries on these issues, and debate was going on. Then atomists at some point entered, providing an answer they thought that was able to give understanding about reality. They were thinking that it consisted of eternal particles moving on empty void. Plato and Aristotle, they were very much against atomists. They thought that change, life, human contributions, more subtle things, they could not be reduced to these atoms in empty space. They could not be explained in such kind of framework. Somehow they believed that matter as such, it was undifferentiated. It had potentiality to be influenced by various forms. And this kind of thinking was going on for quite a long time until in the turn of the modern era, Copernicus came up with the heliocentric view, which gave new space to find out new kind of relations. Kepler's planetary laws and Galileo's research on motion was being done, and then came Newton, who was able to give a synthesis on all these new phenomena which had been found based on gravitational force. And also Galilei, he adopted the ancient concept of atomism, and it was somehow taken, somehow self-evident. It was adopted very easily. These natural scientists adopted it, but philosophers like Descartes and Leibniz, they could not take it as such. They argued for a full space consisting of continuous substance, but natural science, they adopted an atomistic view. And even if philosophers and physicists, they all contributed to the creation of a new worldview, somehow metaphysics soon disappeared under the empirical practice. It was no more noticed that this atomistic view, it is metaphysics. It is no physical fact. And because of this revolution, it was assumed that reality consisted of matter in motion. It was material, mechanical, and there was no place for mental phenomena, religious ideas in the realm of science. Reality was comparable to a clockwork. And of course, this kind of thinking, it is in sharp contrast to the perennial view which had been in many cultures. The reality is thought to be one system which contains humans also. It consists in different kind of layers, material and more subtle layers in of course different kind of systems, but the basic idea is the same, one system which contains also human beings with all our mental qualities. But nevertheless, even if it is difficult to explain many things, the particle mechanistic worldview was taken to be true. It was based on solid mathematical theory. It was confirmed by empirical observations. And these metaphysical presuppositions, atomism, determinism, reductionism, objective external observer, they were adopted as real. They were real features of reality. And of course, this was a very good framework. It was able to explain many things, and many kind of problems could be solved in it. It was able, on it was based the huge technological progress that has been going on during the previous centuries. So world was changed because of this world view, and of course the methodological principles it provided. Even if there are difficulties to explain how humans are related to nature, and there is this split between two cultures which is still existing between sciences and humanities. People in these different fields, they have difficulties to understand each other. And we know that objective reality, it is not immutable. And in future, it is going to change even in a more rapidly. So it is quite obvious that humans do affect the course of evolution, and we need a better map of navigation so that we are not acting on wrong basis, imagining the reality, wrong kind of reality, continuing living in a kind of mechanistic, materialistic world. Because in physics, of course, this kind of Newtonian framework, it was not enough. It has not been enough for 1 century. Quantum physics collapsed the familiar worldview. Quantum phenomena can't be understood within the particle mechanistic context. There are different kind of phenomena. And the interpretation discussion, it has been going on for a century. There are many kind of interpretations which all imply profound changes to the worldview. There is no possibility to choose the right one, as I already explained. No empirical tests. But the discussion that is going on, it gives an idea that ultimate metaphysical questions are now discussed. We are once again in a position when natural philosophy is needed to explain new phenomena which has been found, in what kind of reality they could be understood. Because no one anymore knows what's the basic stuff, everything is made up. Is it atomistic or continuous? What kind of relation between the parts and the whole is the meristic, atomistic idea at all? intelligent? How do the object and their properties emerge? What's the role and locus of humans? How we are related into the nature? And in this kind of situation, it is quite natural, according to Thomas Kuhn, that a new kind of ideas may come up. There may be a major paradigm change which change the rules, raise up new questions, categories, distinctions. Duck may be seen as a rabbit. So even if we have the same facts, they can be understood in a new kind of manner. And in that kind of paradigm change, many old problems and disputes, they just may disappear. They don't exist anymore in the new context. And modern physics, it was enough to falsify the Newtonian worldview, but it has not been able to provide an alternative. And it is very much, I think, because theory of relativity and quantum physics, they are incompatible, as we have already today heard in many talks. And I think physical understanding related to the basic principles of reality, it is not likely to proceed before they will be unified. And one reason for that the new worldview has not been provided is that the ontological content of abstract mathematical theories, it is vague. They are very difficult to interpret. If we speak about many dimensions and very complex mathematical methods, they are only some specialists can understand them. And they are also in different kind of dealing with quite specific issues, and we don't have general understanding in what kind of reality we are living. And because the theories, they are so different kind of theories and the common basis is missing, they are often considered just as operational tools rather than realist portrayals corresponding to reality, as was believed before, because Newtonian theory, it could be understood on the basis of these atoms, bodies moving in space according to certain laws. But this operational attitude, it undervalues conceptual matters, which may be essential for detecting real causes and connections for the observed phenomena. And I think this realist pursuit, trying to understand what is really going on in reality, it depends very much on conceptual clarification. And of course, it also depends these abstract theories. You can't give a conceptual clarification if you don't have the theory. So formulation of a plausible worldview, it is a creative task that demands this appropriate mathematical model conforming to observations and then philosophical talent to provide a sound metaphysical context. And what is my claim? That dynamic universe is a good candidate to provide further understanding about reality at very fundamental level. And there we have mass, very abstract quality as such, which begins to move because of its own gravitation. And this mass, it is closely connected to space as a surface of a four-dimensional sphere. this mass that gains motion, and it can be further energized in different kind of processes going on in nature, but its amount always conserves. And then we have this zero energy principle, which means that sum of motion and gravitation, it is zero always. So basically, out of matter and nothing but this zero opposites, everything comes out. We have a pendulating, self-organizing whole in continuous chains. There is a seamless connection between mass, space, motion, and energy. All the seemingly separated objects, they turn out to be internally interrelated. So this is not a mechanistic model at all. There are basically no separated particles. All bodies can be constructed out of waves. And compared to the relativity theory, the state of motion does not affect time or spatial coordinates. And it gives the possibility for the energy to conserve, as Tuomo Suntola explained in his talk. And this mass, which is the basis of everything, Newton took mass to be a property in the bodies, and there was this force between bodies and mass, but he was not able to give any reason, any cause for gravitation. But here, mass is the hidden basis of everything. It's the foundation of all existence. And because of gravitation, mass entails movement that provides potentiality for everything to actualize, for an evolving universe to manifest. And energy and mass are not to be equalized, as already was said before today. All forms of energy are originally derivable from mass and its movement on the third dimension. And mass is always conserved, whereas the sum of energy is always zero, so you can't identify these concepts. And some more ideas about these philosophical or theoretical virtues, or how you want to define them compared to standard theories. As I maybe already said, DU is more encompassing theory, which is built on a smaller number of premises. It covers the observed facts, but it does not seamlessly fit into the previous lines of thoughts, and that's the reason maybe why it is quite difficult to accept this kind of theory, which does not fit into the context where physics is nowadays done. But according to the ideas of Thomas Kuhn, this is inevitable. In a paradigm change, new kind of context is being born. It provides answers, or it can predict all the phenomena which can be observed, if it is good enough, as this theory seems to be. It gives a new kind of context. And one virtue of this theory is, of course, that it does not need any ad hoc hypotheses to fit with the observed results in physics and cosmology. And in a wider ontological framework, many present concepts, such as dilated time, dark matter, energy, turn out to be mere epicycles, just like in the Copernicus system, the epicycles were just realized to be not real, they were mathematical constructions, and in the context of DU, there is this fourth dimension, a metric dimension, which gives more space to detect new kind of connections between these basic concepts, mass and energy, and movement and things like that. And it has very clear principles, it has transparent mathematics, so this theory can be quite easily interpreted like Newton's synthesis at each time. This precise model includes an obvious ontology which can be spelled out into unambiguous interpretation. It provides a more natural perspective to cosmos. And in this kind of reality, invisible and change are naturally present. There is this fourth dimension which somehow binds everything together. Motion in space is related to the primary motion of space towards the fourth dimension. And there is continuous change going on. So everything is historical in the sense that there is time and a context which affect what can be observed in every given circumstances. But this is not deterministic in that sense that it is like a clockwork, like Newtonian system. This is a lawful system, but it is much more flexible. There is room for Aristotelian kind of potentialities and the activity of human beings to affect the course of evolvement. And this zero energy principle and mass, they prevail everywhere, determining the whole space, so they give the context in which everything evolves. And when particles, they are just secondary constructions, mass and space are very closely connected together. This fits quite nicely to the ideas of undifferentiated continuous matter that was assumed by Plato, Aristotle, Descartes, Leibniz, the biggest philosophers who tried to understand how human qualities and mentality is possible to understand. And I think that in the context of DU, the age-old schism between materialism and idealism can be solved into a synthesis. The whole of existence is based on mass and its energization, and in complex systems, there may also be more subtle forms of energy, and the phenomena we call mental or spiritual, they need not be disconnected from the totality emerging from mass and its energization. So there is no need for Cartesian dualism, and the whole supports material as well as mental phenomena and binds them together. And it is not difficult to understand how human beings with all their features may be a result from natural evolution. We, like everything else, are born into certain historically determined frames that provide as well as limit the resources and possibilities that are available in given circumstances. And whenever humans use their resources to modify something according to their intention, we may say that a new form has entered into the substance, potentiality becomes actuality, and when this is what happens, it is unavoidable ethical challenge for us humans think what to actualize, how to understand this reality we are living in. Is it just a mechanical system, or is it some kind of self-organizing complex reality which can be described by this dynamic universe model? And if this is the proper model or not, I think we humans, we are never able to describe whole reality. No theory is able to take in everything, but nevertheless we may be proceeding towards better descriptions and understand reality in a more complete manner. And this is what I think happens if we accept this theory, or anyway, it should be properly studied if there is some mistake, which I maybe have not noticed, but anyway, I think it is really worth studying properly. Thank you.
Now I think it's good time to proceed into the panel discussion. Okay. So, any questions?
Move closer to the,
Classical physics and quantum physics, could there be a third class of physics? Is it an explanation of everything? Is that the final stage?
Can you repeat the question?
Yeah, we had the old classical physics, Einstein, and now we talk about quantum physics. Could there be a third class of physics, the final stage?
There's only one physics. I mean, the classical physics is, you can derive that from quantum mechanics. I mean, there's only one physics. The different theories at different levels, okay? So classical physics works, or Newtonian mechanics works on the macroscopic level, and then there's a microscopic level where the quantum mechanics kind of things work. But it's the same physical theory. I mean, I wouldn't call them different theories.
All right. Any questions in this row here?
Can I comment, make a comment?
Oh, please.
I've heard some people, not here, but I've heard people refer to quantum physics is completely different from, classical physics. But I agree with Tapio. And if you look at the history of physics, if you look at Schrödinger's first paper, for example, he starts out with something that came out of classical statistical physics, the equation, the S equals K log of the of a distribution function. But he interprets it differently, and he comes up with what we call the wave function and the time-independent Schrödinger equation. So it's not this idea of quantum physics, it's like nothing you've ever heard of, you can't understand it, it's a new paradigm. That's nonsense, I think, from what I've seen. In fact, if you look at the conservation of energy, for example, in the classical, this is something I alluded to in my talk. One way of getting to Schrödinger's equation is you take the classical physical property and the symbols you replace those symbols like momentum with an operator that is a derivative of something. Okay, And then you get the Schrödinger equation. That's not the way Schrödinger did it, but it just shows that there's an intimate connection between classical and quantum physics, which is all part of physics.
Can I make a very short comment? A straight answer to your question, in which I disagree with my colleagues here. I do think that there will be a third class of theory, which is not the present classical mechanics and which is not the present quantum mechanics. There will be a third class of theory, which is a modification of the Hamiltonian dynamics, which will be the mother of all mechanics. And both classical mechanics and quantum mechanics will come as separate approximations from that equation. That is a straight answer to your question. This is what I will predict with confidence.
It is my philosophical belief that all the theories about the nature has to be consistent. I would not say it's a unified theory. For instance, the theory about the atomic physics and the theory about the solar system can be completely different. Statistically, the physics of a thermodynamic ensemble is quite different from the physics of a single particle. But the unification or consistency should be understood that different theories should not have direct fundamental inconsistencies, regardless of what field you are in. For instance, if somebody who studied geology or physiology come up with a theory that's in direct conflict with celestial mechanics, there's a fundamental inconsistency, then one or both could be wrong. And you got to resolve that inconsistency. So my understanding of the unified consistency, it doesn't mean a theory for everything, but there should not be inconsistency or fundamental inconsistency between any theories. As to the concept of having two different physics, macroscopic versus microscopic, I think we should not ignore a fact that there's something fundamentally different between the microscopic physics and macroscopic physics. Otherwise, there would not be a lengthy, consistent, and persistent debate between Einstein, Schrödinger on one side, and Copenhagen physicists headed by Max Born and Heisenberg on the other side. These are not laymen. These are experts. So there is a fundamental difference there. We cannot just turn our head and bury into sand and not knowing this. For instance, about the renormalization of quantum electrodynamics, which is a norm of the particle physics. We have an expert, Paul Dirac, who did not like the idea at all. He thinks renormalization is mathematically ugly. Later on, when quark model was presented by German, a famous physicist, Feynman, did not accept it. And it took him 30 years to accept quark model. And nowadays we have a superstring theory, a quantum gravity, and all these theories, it's also known as theories beyond the standard model. That's not accepted by the leaders of the mainstream theoretical physics. For instance, Grashow, who is one of the 3 Nobel laureates for the Standard Model, he simply dismisses the superstring theory as theology. So there's something fundamentally different, and that's indication that there's something we don't understand. The positive attitude is try to find out what is it, what is right or what is wrong. If both are correct, there got to be some connections in it, and that's my understanding.
Before we continue, maybe good to say your name, maybe affiliation, and if you direct it to special speaker or it is a general question. So please.
Yes, this is a general question, but maybe for Professor Gold. My name is Jens Tonstad. I'm just a curious computer guy looking into this stuff. I noticed you mentioned in your talk the de Broglie wave theory and Bohmian mechanics. And I was under the impression that the Bell inequalities had sort of invalidated and buried that theory, but it seems to be coming back. Is there a way out so that it can be resuscitated, so to speak?
Is there a way out so that what?
Is there a way out so that the Bell inequality doesn't kind of bury the pilot wave theory and yeah.
You mean so that it's not true that the Bell inequality is no longer true, or?
Yes, or there's another explanation so that it doesn't necessarily result in that hidden variable branch of quantum theory being impossible.
Well, if by what you mean by a way out is there some way where we don't have to concern ourselves with things like hidden variables? Is that what you mean by a way out?
What I meant is I was under the impression that the Bell inequalities had made that particular branch of quantum mechanics impossible. And then there was I read that the many worlds theory was maybe a solution to that got around the problem of the Bell inequality.
Tapio looks like he's...
Look, I don't know what you've been reading, but I mean, the Bell inequality exactly tells us about the entanglement. It tells us about the quantumness. And that's exactly the point, that if the Bell inequality is violated, this cannot be done with local classical hidden variable theories. So it is a direct measure of the quantumness. And in fact, it's very easy to show that almost all entangled quantum systems violate Bell inequality very easily. So it's a useful tool. We're actually using it to find about entanglement and quantumness. There's nothing, that's exactly the point. Quantum systems do violate Bell inequality because you cannot have classical correlations that would violate it. So it's the quantumness that violates. The quantumness I was talking about, the entanglement. That's perfectly okay. So I don't see what the problem is. It's a measure of quantum correlations.
I think he was asking whether, since de Broglie theory is a hidden variable theory in the sense of position being the hidden variable, he was under the impression that such theories are not allowed because of the Bell's result. I can clarify that.
Okay.
Bell's result pertains only to hidden variable theories with the locality assumed. That means things like wave particle duality, wave function, so on are not part of such theories. These are hidden variable theories which are like classical statistical theories. The de Broglie theory, on the other hand, uses a wave function explicitly. It starts with the wave function of quantum mechanics. It's a non-local theory. So de Broglie version is a hidden variable theory with non-locality as an essential component. Therefore, it doesn't obey the Bell's inequality. So therefore, it is out of this restriction which you pointed out, it comes out of that.
Also, I wonder what you mean by hidden variables. Do you mean variables that haven't previously been used in describing physical processes like momentum, velocity, energy? What are hidden variables? See, because if you mean things that that haven't been used over the history of physics, new quantities have come up. The particles have spin in a way, but spin has a different meaning for quantum physics than classical physics, in the sense that in classical physics you can think of something that's rotating around an axis, but in quantum physics there is not a continuum of values for the spin. That is, if you think of the rate of rotation, there are discrete values that can be taken on by electrons. So in that sense, you could say that spin in the quantum world is now a hidden. It was a hidden variable, but it's no longer a hidden variable.
Determining them at the deeper level, which we haven't kind of uncovered yet.
You're asking about your indeterminism as being associated with hidden variables. That is, if you can't determine it, then it's hidden.
Oh, it could be hidden. Either there has to be indeterminacy, or it needs to be deterministic at a level which we haven't yet been able to understand. But yeah, thank you for the answers.
Yeah.
Hi, yeah, my name is James. I have a question for Tapio. I guess you had mentioned this current generation of quantum computers using pretty cool quantum phenomena. And the previous generation hadn't really used quantum things. And I was wondering whether you can just clarify that a bit, because you had a picture of a transistor and people often talk about tunneling and things. And I'm sure you have an explanation for that as to how that doesn't qualify as, quantum phenomenon.
Well, this is exactly the point of physics, right? So the physics is a layer of theories at different levels. So we have the fully microscopic level. We probably have some more fundamental theory that we don't know. Then we have a quantum mechanics. You coarse-grain quantum mechanics, you get classical microscopic theories. You coarse-grain classical microscopic theories, you get what is known as continuum theories, like elasticity and fluid mechanics. Those can be derived from microscopic dynamics. So what I mean by quantumness then is that I define true quantum devices or quantum technology as such that you cannot describe by effective classical theories. It's as I said, you can't simulate them with a classical circuit. Like you can one particle quantum mechanics, you can simulate, you can mimic with classical stochastic, so classical random or stochastic circuit, but you cannot do that for entanglement. So the new devices specifically use both quantum coherence and entanglement. Actually, these two things are related when you have more than one particle. Okay. So again, if I describe the operation of my computer, or it's just I don't know, any electronic equipment currently, I can mostly describe it with classical circuits and classical, basically, classical theories, just relating currents to voltages and things like that. So I don't have to worry about the quantum mechanics that's actually somewhere in there at the microscopic level controlling the motion of electrons. But again, the point is that these devices do not use quantum coherence or entanglement. The new ones do. So that's where I draw the line. You can define this in a different way, but I think it's a very consistent way of defining what I call the new quantum technology, devices that use coherence and entanglement.
Maybe I can help to clarify the difference. Professor Ingthorsson, in his presentation, has a keyword, quantumness, right? Which actually means entanglement and interference.
Right.
In classical mechanics, classical quantum mechanics, wave function was not taken seriously. Maybe that's not the good term to say it. In classical quantum mechanics, wave function is just a mathematical tool. Itself is not measurable. You use that to find out what is statistical average of it. But in quantum entanglement effort, which mainly includes the communication, quantum communication and quantum computing, wave function is taken seriously. Wave function is not merely a mathematical tool, but it's a physical quantity and object that you work with, and you take it as object.
That's a good.
Yeah. Okay. Point, yeah. Although I have my serious reservation to it, but I try to clarify this. Yeah.
Well, they do work already. Like I said, you can come to Aalto in maybe next year and you can try our little computer if you not believe that it works.
Okay, maybe next question.
Well, thank you very much all for your nice presentations. My name is Dimitris Zarouchis. I'm affiliated with Aalto University. And actually, I do have a question for the dynamic universe people. Oh, let's switch some gears. Actually, I have to declare my total ignorance about that theory at all. Of course, I'm not a relativistic guy or cosmologist or something like that. I'm just doing electromagnetism. So I have to express a question, but it is rather a skepticism hidden behind it. When someone shows a new theory, even within the Thomas Kuhn context of paradigm shift and trying to reconcile old controversies or existing misinterpretation of data, etc., then of course needs to support his or her own construction. Right. So I saw very nicely you presented in actually 3 of the presentations, 2 of those being in the more technical side and the last one being in the more philosophical aspects. I saw only success. I mean, I saw a few examples that supposedly that theory works. And naively, I believe you. However, I have 2 questions that has to do with the approval of the community. Okay, so when someone claims about a new theory, then the first step is first of all to re-examine old problems under this new perspective. This is number 1. And number 2 is to express these achievements in a wide audience of physicists that they do work there. And since I don't know, how what is the acceptance? Have you talked about that theory in wide audience in physicists or in people that are more related to that? And what was the reaction there? Or I cannot just simply believe that is too perfect. Is there any blind spot or is there any trap or any, let's say, catch? Because every theory in the history of theory, I mean physical theories mostly, they do contain also intrinsically some blind spots there. I would like to hear a comment, actually. Thank you.
Yeah, I'm not sure I got all the questions, so that may I check that you like to hear the general reactions to the dynamic universe and how to introduce that to the greater public and the scientific community and that kind of things. Was that? Theory has been exposed to the general. Yeah. that's a very, very difficult question in a sense that there's very high resistance of accepting this kind of major shift in the paradigm. So that, in fact, I haven't got a scientifically well-based opposition against the dynamic universe. There might be individual experiments which are said to be against, like the one what Tapio Ala-Nissilä presented here. I am not familiar with the experiment, but the interesting thing there is that the audience that best adopt this kind of thinking comes more from practical physicists, so that I have got very high support from industrial physicists who work with practical issues and like to understand. So it's a kind of technologist attitude to try to understand what is behind the theory. And the theory that opens the connections to the real world is then far more usable from that point of view. For example, the question of expanding local systems. Tapio Ala-Nissilä stated that there is some satellite measurement mainly for strong equivalence principle. Was that correct?
Yes.
Yeah, that's a little bit different thing than the local expansion. On the other hand, Heikki Sipilä presented very strong evidences that supported the local expansion together with the whole. And perhaps the strongest opposition that I got was about 1 year ago in this same hall when we discussed about the phenomena observed in planetary systems. We discussed about similar things that Heikki presented here today, was by an astronomer who simply stated that it can't be that if that were true, all the books on astronomy would be wrong. So that, of course, yeah, I think he's right. Personally, I think that perhaps the strongest support on the, let's say, uniform expansion extended to all gravitationally bound system comes from the measurement that I showed you here, which is the angular size of galaxies. So that clearly the observations show that it's a kind of Euclidean appearance, and that's possible only if we assume that local system galaxies and other local gravitationally bound local system quasars expand in direct proportion to the expansion of space. So that's what I feel is the strongest support. What I can add to Heikki Sipilä's list is the analysis of old solar eclipses. So there are astronomical data available from old Chinese measurement notes and also from some of the Arabic area back to 2,000 years. And the only way of getting the match with observation was to take into account the expansion of the solar system. So that was very, very strong evidence also. So that in general, I like to have more like a humble attitude concerning the choice of the theories, because what we like to learn, the attitude, we should have the attitude of trying to understand. And with this attitude, we have to study the different alternatives until there's such a, let's say, covering general match with the different areas, and then we can consider that perhaps now we are on the right track. So we can't draw the quick conclusions from individual measurement. We must remember, for example, measuring the equivalence principle or strong equivalence principle. We are very strongly dependent on the conspiracy of the laws of nature, in the same way as we measure the velocity of light with atomic clocks. Atomic clocks are the frequencies directly proportional to the velocity of light, which guarantees the same result whenever we do that measurement. So that it is extremely demanding task to analyze the test results. So I've been doing that analysis now for more than 20 years, and I noticed that in many cases there are kind of hidden factors which must be found out before we can make the final judgment of the analysis. So that this is a very tough question. A nice thing with which I've been very happy of is that mainly people, which is a very relatively small group, who have the patience of studying, understanding the theory. There then has been no way back. So I have no feedback that after analyzing, after becoming familiar with a thing, to show, let's say, scientifically meaningful critiques on that. So that I think that's a good sign. But I'm not saying that that's the only way. What we can be sure of is that the reality is what it is, and each model is able to describe a part of the phenomena observed, or it can have a higher coverage, it has better accuracy in some area, but there's no single truth in building, in constructing the theories, so that what I've been looking for is to have a more holistic view, and being surprised, for example, in this case, how far I've been able to get to understand also the details. But I'm not sure that this will be the final theory either. So that we'll see how far we can get with that, and the time will show, not probably during my lifetime, how this kind of theory will be more generally accepted, so that maybe our grandchildren will tell for those who live at that time.
Oh, thank you.
Let me clarify the experiment. So this experiment on the expansion of the solar system has been going on for the last 10 years by satellites. It's an extremely intricate, complicated, sophisticated, and precise measurement. And in fact, one of the geodata gave 1.5, and this new data absolutely gives 1.5 centimeters per year. This takes into account all the planets in the solar system. It takes into account models of the sun. In fact, there's a big effect from the non-sphericity of sun, the fact that sun is actually not spherical. That actually affects the gravitational field and affects this number. So all these effects are taken into account. It's an extremely complicated calculation. You have to take many, many effects into account. You can't describe them with a simple equation or a single theory. That's what it is. You read the paper, it's in Nature.
Yeah, it's very, very alarming to have a test which is very complicated, so that
physics
the simpler the test and the simpler the theory behind, the better I feel it is, the more reliable.
Two questions, if I may, to whomever wants to answer the first one. Another about simplicity. Some theories have lots and lots of fundamental particles and dimensions and whatnot, where with enough parameters you can fit basically anything you like to, but it's easy being any effective in explaining anything, which in statistics is called overfitting. So do you think that theories that postulate more and more particles or dimensions are a case of overfitting the data? You see what I mean? And question number 2, what do you think personally is the biggest scandal or the biggest problems in the mainstream business of unification theoretical work? Did you get the question?
I don't get your second question.
The second, what are the biggest problems in mainstream theory?
What is the biggest problem in mainstream physics?
Yeah.
Okay. Let me respond to the first question about the too many parameters in theory, right? Let me share with you a story. This is commented by Fermi, Enrico Fermi, the father of nuclear energy, right? Freeman was another important figure who proved that renormalization it can be systematically done. Freeman was, when he was young, he came up with a theory to explain Fermi's experimental results. And he was so excited, he took a Greyhound bus to Chicago and tried to get his approval. Fermi knew his theory a little bit, but he did not mention anything. He just showed hospitality and talked about some other stuff, non-physics. And Freeman was not patient. He said, Professor Fermi, how do you think about my theory? I explained your experimental data beautifully. And Fermi was going like, how many free parameters do you have? Right? He said, well, 4. Fermi said, my friend Van Neumann used to say, with the 4 free parameters, I can fit any data into an elephant. Give me another one, I can make his trunk wagging. So that's actually a classical wisdom. With too many free parameters, it's quite a skeptical if the agreement is an indication that your theory is correct or it's just a result of fitting, statistical fitting. Now compare that to the standard model of particle physics. There are 19 free parameters, right? And this actually is known in the particle physics community to be one of the very important issues. You know, if you are a statistician, your common sense would tell you a model with 19 free parameters just doesn't make much sense. So I hope I respond to you on that matter.
Well, you just confirmed my...
Yes, confirmed your suspicion, so to speak, or skepticism. And actually, I share that with you. To the second question, what are the main problems with the mainstream physics? Let's look at both sides, the macroscopic and microscopic. In macroscopic side, the Big Bang cosmology dominated the study of macroscopic world. You have all kinds of brands of it. You're talking about a dozen different brands. Even in the current model, you have all kinds of fundamental problems. The well-known, we can list like a horizon problem, which says that the universe was expanding with a velocity higher than the velocity of light, which is in direct conflict with relativity, upon which Big Bang theory was built. Another is the geocentric nature of the model. Another thing is the stunning discrepancy of an important or the most important prediction by Big Bang model that the mass density of the universe is 30 times greater than what is observed, right? And then in my mind, that single prediction is sufficient to falsify the model. However, the issue was politically solved by declaring that 90% of the mass is dark mass. It's like a fortune teller. I predict that you have $1 or €1 in your pocket. But if you check your pocket, it turns out to be only 3 cents. I then declare that 97 cents is dark money. How would you make that fortune teller? Right? So on the microscopic world, we know that the ultimate goal is to come up with a theory of everything. That is, not only you can unify weak interaction with electromagnetic interaction, we also would like to unify strong nuclear interaction and hopefully gravitational interactions. Now, all the effort to unify the strong interaction had fundamental problems. For instance, such theory predict that proton will decay, but all the measurements shows that the protons have at least a long lifetime of 10 raised to 38 years, which is 25 orders of magnitude longer than the lifetime of the Big Bang universe. So practically, proton doesn't decay, electron doesn't decay, right? And the strong interaction is a highly nonlinear equation, nonlinear theory. There's no approximation you can do, and there's no way you can draw easily the Feynman diagrams. Experimentally, you would need an accelerator greater than the solar system to check if this theory is valid. And if you use the philosophy that if your theory is not falsifiable, it's not a scientific theory. Now, the unification of strong interaction demands an energy of 10 raised to 16th GeV. If you want to unify gravitation in it, you need an energy of 10 raised to 19, which is 1,000 times higher than what you would need to unify strong interactions. And from the theoretical point of view, it is generally realized that the gravitation is incompatible with quantum theory, so to speak, in general. So we see there is a fundamental gap between different theories. We cannot bury our heads into sand. So I don't know if these few examples would answer your question that where the problem is. If there's no problem, we don't have to worry. Because there's a problem, like some of the presenters here said, somebody got to do it. Right? Somebody got to say, I do not see Emperor's new clothes.
Let me make a comment.
Thank you. That answers very well. Unless someone else wants to give additional problems that they see as the most. Oh, thank you.
When you have different theories, philosophy comes in part, in the sense that if you have contradictions between the theories, that has to be resolved. And so, for example, in relativity, you have, and this gets back to the question that I asked you that you could answer here. We talked about it briefly, where you have a conservation of energy, a certain scale, right? And then there's a change of energy into matter or matter into energy. Okay, so this is something that I asked about, and there seems to be a contradiction between relativity, as it's known today, and what you're maintaining, namely that you can't talk about the equivalence between matter and energy. Okay, so maybe you would. So we have a contradiction between the two theories here, right?
One is relativity.
One is relativity, the other is yours.
Not mine. It's actually Newton's. Thank you, Professor Gold, for raising that question. It's really important. I said it explicitly, without any diplomacy or politics, that mass and energy are different physical quantities. But in modern physics, mass and energy are considered equivalent. And Professor Gold actually raised an example that this pair production or annihilation is used in clinical practices, right?
Well, no, the example I gave was a PET scan.
PET scan, yeah.
PET is an acronym. It means the positive emission transaxial tomography.
Yeah.
It's used as a diagnostic tool.
Yes.
And the way it works is that you have the patient is injected with a mild radioactive substance, which emits positrons. And when positrons get together with an electron, and electrons are all over the place in the atoms of our body, then the electron and positron annihilate and give rise to gamma photons, okay? The gamma photons are a different kind of stuff than the positron and the electron at a fundamental level, in the sense that the positron and the electron can be at rest. They have mass. Okay, they have what is called rest mass. The gamma cannot be at rest, and so you can make a distinction and say, well, now the gammas are a form of energy, okay, which were a form of mass, because the mass was coming from the electron and the positron, and so that would fit in with mass and energy are two forms of the same thing, okay? So that's what I was saying.
Yeah. As a matter of fact, one of my friend or classmate in graduate school is working on that exactly. He is using PET to diagnose patients. After reading my paper, he sent me an email. He said, what if there's no annihilation, then my equipment may not work. And it's a matter of life and death to my patients. It's so serious. Here is a typical case that how do we interpret a phenomena? I assured my friend, I said, you keep on using your PET equipment, you won't have any problem. It's not going to cause life and death. The issue is, what you can observe is that you inject or inhale some radioactive isotope in your body. And what you observe is actually a coincidence of 3 photons. 2 of it is supposed to be created out of annihilation of a positron with an electron. You have electron anywhere in your body, so that's no problem. and with another photon that's accompanying the production of positron. So here we have observed the phenomena, and you have interpretation. There are actually two hypotheses here. One is that radioactive isotope will disintegrate to emit a positron and a photon, which is not directly observable. Then the second postulation is that this positron will find collide with any electron in your body and emitting two photons. So this, again, is not directly observable. Now, then you will ask, then how do you explain? You inject or inhale a radioactive isotope, and then you can observe three photons. What is in it? It's a smoke. It's box. I have no explanation of this. And then there seems to be mystery. But to me, no mystery is more mysterious than creation and annihilation. So if you want to show directly annihilation or creation, you send a beam into vacuum. And if you can knock out some electrons and positrons, I believe in creation. If you let the positron and electron collide directly, and you observe a pair of gamma photons, then at least that's a direct experiment. So what you're saying that there seems to be a plausible story that can explain why this radioactive isotope can generate three photons can be considered as a support, but not the proof of creation and annihilation.
This is,
Thank you.
I'm talking about something that's done in particle physics. I mean, the particle physicists have creation, have annihilations. Actually, it's two photons in loads of experiments. So I don't think there's anything mysterious about it. But I think it addresses the problem of the claim that matter and energy, as you put it, are not equivalent. You know, that E equals mc squared. And I'm not referring to it, it's true because it's a famous formula, but
I know it's famous.
I've seen it, I've used it, I've seen it in use, and I think there's plenty of experiments.
It's shocking,
Plenty of experiments to support it. So I don't understand.
You can see a famous picture in the textbooks showing the creation and annihilation. But all these photos are taken in either steam chamber or whatever, which is filled with gas, either sodium or with hydrogen. You cannot have this phenomena taken or happening if there's a vacuum. So it's actually a photoelectric effect.
No.
It is, or secondary electron.
You have back the.
Maybe we could proceed now.
Sorry, okay.
Yeah, okay. Let's proceed.
We may have a lengthy talk.
Thank you.
Question there.
We have 5 questions more, so I suppose that we go to question-answer mode forward.
Hello, my name is Raimo Partanen. I'm a member in this society. I'm interested about medical science and new diagnostics. And I wonder if this new physics and quantum theory and quantum computer can speed up the methods of diagnostics in medical science. Medical science is getting new theories and new science all the time, maybe fastest in the whole world. So I wonder if you know anything about these methods and how they can, how this new diagnostics can be become more speedy in future? Thank you.
Well, they are already using this for drug design. I mean, that's the most immediate computational drug design. That's the most immediate application. And certainly, I think in the machine learning, which is sometimes falsely called artificial intelligence, there's no intelligence there. Quantum computer will have huge potential in diagnostics and other things like that. But drug design is already being done.
Question? Oh, do you have? Okay.
Okay, thank you. So my name is Esa-Matti Park, and I'm a radio engineer, so not expert on theoretical physics. First, I have one comment and then one question. So one comment, there was a question about this, about how this dynamic universe theory has been made available for public and of course for professionals. And I know that anybody can download it from the internet. And I think that what Tuomo and basically we all are waiting that the theoretical physicists, they would start the discussion properly. I think that has been not started, and I think the explanation is very clear. They are also only human beings. They have been using whole their career to protect and try to prove that.
You're incorrect.
No, okay, maybe incorrect, you can correct. But there has been no proper discussion.
There has been.
It has been? Yeah. Okay, maybe you tell that also. Then the next my question, yeah? And it's to you, Tapio, and you talked about this entanglement of the quantums, and maybe you could explain, because I've understood that when you entangle that, then basically the characteristics of those two quantums are the same. So, or let's say so that when you measure the other one and you change the state, then the other one will change also the state to the same. And on the other hand, I've understood that the observer also has an effect on the object. So when you measure, you may change the states or whatever. So how do you then find out the other one has changed the states without actually measuring it? So thank you.
Okay, so again, this entanglement means that you get something that is not a sum of the two. Okay, it's more than the two. And that remains when you separate them carefully. But of course, once they have been separated, then eventually they have to become the ones that they were. Say spin up and spin down, right? So then you know that they both carry this information. And because originally you combined one with spin up and spin down, then if you separate them and then you measure one of them and you find, okay, that was spin down, then you know that the other one, since it's now alone, has to be spin up. This is quantum correlation. So is there anything funny? The only funny thing is that this correlation remains, but it's a very delicate thing, right? So any little perturbation, disturbance can destroy that, and they get back to being what they were. But again, since both carry this joint state, then you don't know which one, if you measure one, you don't know which one it's going to be. It can be either up or down, but then you know that the other one has to be down. But so nothing is violated. I mean, because to tell the others, because the others who don't make the measurements, they don't know before you tell them, right? So, and for that you need to send information. So there's no violation of causality or anything like that. No physical principle is violated. It's not that complicated. The only funny thing is this quantum correlation, which you cannot classically describe.
May I add something? There's a famous experiment called by Allen aspect. And you have, I think it was a calcium atom, and there's a decay, and two photons went off in either direction. And if one photon is measured would spin up, and you say, well, the other photon should have spin down by conservation of, say, angular momentum. So you can think of it that way, but what his experiment does is that near the detector for one of the photons, you can change things. I think it was the polarization. And you can change it in such a way that if this then is detected to be spin up, this one is detected to be spin down. But if there's a transmission, it's faster than the speed of light, okay? So this seems to be tied up with these correlations. You know the experiment that I'm talking about. And therefore, it's not just that if one spin up, the other spin down, but you can play with the polarizer. I think he used some ultrasound to change the state of this photon, and this one follows suit. So you do get this. You get a conservation. As far as they are apart.
Next question from the left.
My name is Timo Karjalainen, and I used to invest economics and social sciences, in which I learned that 5 plus 7 is not necessarily 12. It means when Mr. Wang introduced the idea of black money, I don't remember, was it 90% or 95%, but anyhow, in economics, it is quite clear that we cannot count on mathematics very heavily. It is not necessarily true. How is it in physics? Do you still believe that the nature is speaking mathematical languages, or the Lord is using mathematical languages? Or is it so, as I think it is in economics, that 5 plus 7 is sometimes 12, sometimes 10, sometimes 20. It depends on the situation. How do you use mathematical languages? What is the relation of mathematics to physics nowadays?
I think there's a fundamental difference between research in physics and in economics. In economics, you largely rely on statistics. That is, you have enormous number of participants, such as the stock market. You will not have stock market if you and your wife alone are living in the Garden of Eden. Two people does not form a stock market or any market. All this economic behavior or marketing behavior are statistical behaviors. And yes, there are some dark hands behind to manipulate the stock market. But this is not the subject of physics studies. Physics studies something objective, something that's there. And I don't know if it's appropriate to say nature speaks the mathematical language, because nature is not a human. Language is something we invent to communicate. That's why we have all kinds of languages. Of course, I know Chinese is the easiest, and that's the only thing I can handle. So in physics, one of the important principle or consensus is that you respect the objective world. You study it. If your theory agrees with the reality, with the law, then your theory is correct. That's the most important criterion. It's classical criterion. Regardless of whatever mathematical form you can come up with your formulas or equations. Yeah, aesthetic beauty is a luxury. It's what we like to have, but it should not be placed as a fundamental requirement or principle. Mathematics is just tool. In one of my publications, I made a statement that nothing is more threatening than a mathematician demand the physical significance for every solution to his equation. Some solutions are not physical. Say, if I give you a volume, say 1 cubic meter, or for a sphere, tell me what is the radius. And you set up an equation, you take a cubic root of it, it comes out with 3 solutions. One is a real number 1, the other 2 are complex numbers. Then you dismiss the 2 complex numbers as non-physical. Choosing the physical solution is a part of the task of solving equation. But if you demand that the other solutions are also physical, it belongs to 2 other universes, then you are creating universes with mathematics. This is a practice of a gentleman called Koivo, who actually started this business of creating multi-universe and a wormhole and black hole and white hole.
Okay, thank you very much. Next question from the left.
Can I make a short comment on that? Very short. See, mathematics is a very convenient tool to efficiently do physics if you know what you are talking about as a physical reality in physics. It is like saying alcohol, consume with moderation. In physics, it is important to use the mathematical tools and techniques with moderation. And I will give you one example from history where a person couldn't talk to nature through the mathematical language but made the greatest discoveries which we use today, Michael Faraday.
A short question from the commoner. How about this strange thing which I call unknown, a lot of energy and unknown matter, which researchers talk about dark matter and dark energy. If you use dark, then you know some properties of it. But for me, it is unknown. And to you, Tuomo, does your dynamic universe include also or have this kind of unknown energy and
in my
matter?
theory, there is no dark matter and dark energy. My universe is not a my invention. It's just classical cosmology. We make less predictions than the Big Bang model could. The origin of dark matter was actually the failure of the Big Bang universe, Big Bang cosmology, in predicting the theoretical mass density of the universe, which turns out to be 30 times greater than the observed ones. So it's politically turned into a new discovery and the reason for further funding. And yes, it has not get a lot of funding to search for dark matter and dark energy. That also is echoed by particle physicists who is supposed to be working in the microscopic world, but the dark matter issue allows the particle physicists to come up with all kinds of weird, whimsical particles. So that actually bridged the cosmology with particle physics. It gains more momentum.
Okay, thank you. And Tuomo, have you something to continue? The question was directed to you.
Your dynamic universe, do you have also some unknown energy and matter?
Well, I'm not sure I understand what you are looking for, unknown energy or matter. Well, yeah, such as dark matter, for example. Yeah. Okay, in principle, we may have non-structured matter. I don't have analyzed that kind of idea in more detail, but it's one explanation for the rotation curves of the galaxies, and that's where. So I feel it's possible, but there might be other explanations for the rotation curves as well, but I can't see how important that is. Unknown energies, I don't have in that. It's very straightforward, because I showed what I call the unified expression of energy, so that we can roughly divide the expressions of energy into the categories of potential energy, the forms of potential energy, and then the energy of motion. And with this we can approach the observed expressions of energy and phenomena. Is that okay? Thanks.
On the right.
Hi, it's been said that if there are new theories introduced, they should speak to the quantum phenomenon of entanglement and explain the double slit experiment. I was wondering whether the dynamic universe would have anything to say about those phenomena. So I was wondering whether the dynamic universe would have anything to say about the phenomenon of entanglement and the double slit experiment, whether it would explain how that happens.
Can you repeat? I simply can't hear.
Sorry.
The echo is such. I use.
So it's been said that.
I'm sorry, I have sometimes problems with my hearing aid. I can't recognize due to the echoes.
Right. So
your question, the question was regarding the quantum energy.
I was wondering whether the dynamic universe would have anything to say about entanglement and the double slit experiment. Does the dynamic universe speak to those issues?
Yes, I have, in my book I have presented, if I had a little bit more time, I had prepared a slide concerning the double slit experiment, so that using the mass wave concept, which can be opened after we have released the hidden C from the Planck constant, then we can describe mass particle in terms of Compton wave resonator. When we put such kind of resonator into a motion, the de Broglie wave is formed as a result of the Doppler effects of the back wave and front wave in the resonator, and the net momentum carried by that wave is exactly the de Broglie wave. So it's a kind of wave following the particle. And so it doesn't then matter which slide the particle takes, because at the screen we get the detection when the kinetic energy, which is carried by the momentum, is converted into detection on the screen. So that in principle it's very simple explanation, but then we need to describe mass particles in terms of the mass waves, so that it's also a kind of a possible illustrative way of looking the wave particle connection.
Okay, thank you. Avril, is there any questions there? Here is one.
Well, I have one, because within the speakers there are some are pro-DU, and some are critical, and some are neutral. But I'd like to ask Tapio that, what do you think are the objective criteria by which we evaluate scientific theories? And then if you evaluate general relativity against DU, so which one is better according to the criteria that you favor yourself?
Yeah, I mean, So this is how physics developed, right? It's an experimental science, empirical science to be more precise. It has to agree with the experiments. Now, sometimes theories get slightly modified by new experiments, sometimes they get rejected. There's a paradigm change like happened with classical and quantum physics, although I would say there's only one physics. It's just a different level of description. So that's all there is to it. Of course, it has to be also mathematically consistent, and it has to conform to all the known physical and measured physical principles, and that's it. That's how physics evolves, and it's evolving right now. So in that sense, something like string theory, physicists think it really is not physics, it's mathematics, because there's no way that we can even think of now by testing the predictions of the string theory. Now, supersymmetry theory, so I'm not a particle physicist, but of course I know what's going on there. So supersymmetry theory, which is an extension of the standard model, has been already tested to some degree, and so far nothing has been found. So at least physics is making progress even in these most difficult or complicated branches where you have to go to huge energies or very, very small scales. And of course, one important criterion is freedom of parameters. I mean, the quantum mechanics has no parameters. There's not a single fitting parameter. All the parameters that appear in quantum mechanics have been measured or determined somehow independently. The Planck's constant, the speed of light, whatever you want to call them, the multiple parameters, and those have precise values, and there's no fitting. Sometimes you have to introduce parameters that you have to fit. I know the standard model has this issue, like you were saying, that there are many parameters. Of course, I don't think they're all free. So often in physical theories, when you don't know how to calculate these parameters or you can't measure them, there are still restrictions. There are strict conditions that they have to obey, and that of course helps a lot. If you have a theory that's just full of parameters, then it's usually, and if this cannot be constrained by some measurements or some other physical arguments, then that theory is considered to be useless because it can predict almost anything if you fit the parameters. So, mathematical consistency, confirming with existing experiments, predicting new phenomena that can be measured, so the theory should be falsifiable. I'm a believer of the falsifiability theory or approach to physics, and freedom of parameters as much as possible. That would be in a nutshell what I would consider my criteria for physical theories. Some other people might have some other criteria, but I think this is mostly what we demand from physical theories.
Okay, thank you for the clear list of these criteria. Now we have from the right and from the left again a question.
My name is Esa Sekkinen. I'm the member of this society, and I'm studying theoretical physics and mathematics in Oulu University. I think, of course, every theory is wrong, at least out of some restriction of validity of this theory. And I see, for example, this dynamic universe model. It has some strong ideas just for the perspective of changing point of view on some thing, but also there is plenty of quite poor assumptions and misunderstandings, I see. But it's maybe valid to scrutinize and discuss in continuing. Okay. Then the question, the developing new theory achievements, I think it cannot be only some geometrical variations or mathematical new parameter using techniques or something like that, but really the changing point of view. And for example, we have a talk about entanglement to change the point of view to this issue can be, for example, why consider particles entangled? Why not consider space-time itself entangled and see these particles just observables like classical objects and so on?
Because we can explain that by simple quantum mechanics. Entanglement is completely explainable and calculable. We can calculate exactly what happens. So why would we need to entangle space-time with it?
Maybe we find some new physics, for example, and so on.
But the measurements have not revealed any new physics. They give exactly what the theory tells you.
But we, when we discuss with the issue of entanglements and so on, we can discuss also gravity, not only quantum mechanics with particles in microscopic.
Well, I did discuss that, right? If you were here in my talk, there are papers now where they show that you can get d-dimensional gravity from d-1 dimensional quantum field, conformal quantum field theory.
Okay,
my
point is only the change of point of view, and this is an example.
Avril, there are some questions? Ready? No?
No ready questions. Any questions here?
I try to...
Could I add something to your question?
Oh, yes.
You asked about the comparison between Suntola's DU and the current pre-gradient theory, right? I confess I know very little about the DU because this is the first time I attended a conference and I start learning your theory. But allow me to share with you the complexity of the current theory on both hands. In the microscopic world, microscopic theory, which is represented by the standard model of the electroweak theory, right? You need a Lagrangian that has 170 terms, and which each term is not just like simple term. Many of the terms, or majority of terms, actually are summation over the 4 indices of space-time. So you're really literally talking about a few hundred terms. How complex is that? On the microscopic hand, general relativity seems to be simple in form because the field equation proposed by Einstein says very simple. G mu nu is equal to a constant, which is A pi times the gravitational constant divided by C raised to the 4th power, and multiplied by the mass momentum tensor. So it's basically G equals to a constant times T. It looks very simple, but in reality, the equation is a tensor equation. It's a 4x4 or second order tensor equation consisting of 16 elements, and 6 of the 16 are independent. So you are talking about solving a set of 6 partial differential equations over space and time. And these are not the ordinary differential equations. It's highly nonlinear. It's a nightmare to both physicists or mathematicians. No one could do it. Einstein could not come up with a single solution after proposing the field equation.
a mathematician, Schwarzschild, came up with a solution only for very, very simple boundary conditions. And you also assume that T is excluded. Assume it's a stable universe. And it's spherically symmetrical. And you also assume that space is uniform and isotropic. Now, people, you hear lots of criticisms against this assumption of the cosmology, that the universe is not uniform, it's not isotropical. Is it or not? It's a requirement. It's something that mathematician has to take. Otherwise, you cannot do anything. It's just not amenable to mathematical analysis. So that's the complication or complexity of the modern theories. So we need to have this on one side and compare on the other side the DU universe, DU theories.
Okay, thank you. Thank you.
General, can I make a comment?
Yeah.
I think September 2015, there was the detection of the gravitational radiation from the collision of massive black holes. And it was written up in Physical Review letters. And the prediction comes out of general relativity. And the devices which measured the gravitational radiation were at different ends of the country. One is Washington, I think, the other is Louisiana. So that plus other tests of general relativity put it on a pretty good foundation. That doesn't mean, like any theory, that we just accept it for all time. But if it has competitors, then the competitors have to do at least as good in their predictions as general relativity has done in its predictions. And Newtonian mechanics, there's a lot of talk today about Newtonian mechanics. It can't account for a variety of phenomena that general relativity can account for. So I don't have an axe to grind about general relativity. I'm just giving you what I have observed and read about the subject. Okay.
A short comment. Since LIGO was mentioned, I'm part of the LIGO scientific collaboration, and I was part of this paper which you mentioned, the discovery of gravitational waves.
About 200 people.
Yeah, so, and I am also part of the group which is building the next LIGO detector in India, LIGO India project. So I thought I will make a comment on general relativity. It is true that it's a very beautiful theory, very tractable theory. All its local predictions are extremely well tested. Its foundations are, on the other hand, only half of them are tested, half of them are still remains as hypotheses. Now there are two very crucial missing things which general relativity cannot explain. And all of you know what these things are. General relativity, nor any other theory in physics, still has any explanation for the pseudo forces which we see daily, centrifugal force and Coriolis force. This truth is not realized by a typical normal physicist, unfortunately. But it's true that we don't have an explanation for the pseudo forces of Newton, either in Newton's time nor in Einstein's time. And this deficiency in general relativity has to be seen very seriously. So I would say general relativity is a very accurate and the best theory presently available, but it is incomplete.
I leave
you.
it to the moderator. So if I have time to respond to Professor Gold's question, I guess it's directed to me.
Yes, please answer about the LIGO experiment.
Okay. First, I would like to clarify. To clarify that the black hole is something that Einstein himself never admit exists. Why? Because it's illogical. What is black hole? Black hole is not just a bunch of dark matter, which is very massive and attract everything. Black hole is defined by the Schwarzschild solution, which at certain value of the radius, which we call the Schwarzschild radius, the solution becomes infinite. It diverges. It's known as singularity. And no one can accept that in physics anything should be infinite. Secondly, when you allow the radius to go smaller than the Schwarzschild radius, then time and space interchanges. Time becomes space, space becomes time. And these are highly illogical. No one could come up with the answer. So 1 month after the solution, Schwarzschild wrote it to Einstein, saying that your equation will lead to a solution with singularity, and there seems to be a black hole there. Einstein never admitted the existence of black holes. And there's some other prominent physicists. I would name one. That's Steve Weinberger. Yeah, one of the 3 Nobel laureates who won the prize for proposing the standard model of particle physics. He has written a famous book. It's called The Gravitation and Cosmology. In his book, he specifically talked about the black holes. He is saying that black hole does not exist in the universe. There's another one, Steve Hawking, who actually was made a prominent physicist. It's known as the most famous physicist after Einstein. The reason for him to win that fame, although not Nobel Prize, is because of his contribution in the study of black holes. It's known as a Hawking radiation and Hawking evaporation. So he spent 30 years there. He was the leader of black hole research. But at his later years, I guess a year before his death, he publicized his opinion that black hole does not exist. It is my greatest blunder to do this black hole research. So after that, I would say that black hole thing is not directly derived from general relativity. If it is, it's something grown from the tumor as a negative stuff. And for the details of this criticism of LIGO experiment, which has also won Nobel Prize, I would invite my friends to check out my publication. I have written an article criticizing the LIGO experiment claim. It's just a common sense type of thing is that how long would you think, would you believe that the collision of 2 black holes would take? Just give me a common sense type of speculation. Wild guess. How long should they take?
Common sense is a tricky issue.
Special sense.
What I tell my students is I ask them what's your intuition about this or that? And then I tell them what I mean by intuition is your belief based on your experience. So if you don't have experience with things like traveling at the speed of light, then you don't have an intuition about it. Now, in terms of black holes, it's a little like the invisibles that Einstein was looking at in 1905. What's the what? Yeah, I'll tell you what I mean. What's the size of molecules? Now you can't see them. Okay, you can't see them. At least at that time, they didn't have atomic force microscopes or scanning tunneling electron microscopes. So what you do is you make prediction. You come up, use a theory, and you make predictions on how these particles that you can see should move based on the existence of these invisible these particles that you can't see. Okay. And if you are correct in your predictions, then the argument is, well, I can't say for all time that there are these invisibles, but it is consistent with my one's view of these invisible particles and the characteristics that they have. So now for black holes, if there exists black holes, then there should be certain phenomena. The infalling matter should give rise to certain kinds of radiation. That radiation should be detectable. You have to predict how much it will, how much radiation you should get. Similarly for, positron electron annihilation, you have to predict how much radiation you can get. And then if you find out that what you claim should happen happens, then that's a confirmation of the theory. That doesn't say the theory holds for all time. Now, it's the same way in ordinary Newtonian mechanics. If Newton's law of universal gravitation is correct, and his second law of motion is correct, then the planet should go in approximately elliptical paths around the sun. Now, you find that the planets go in approximately elliptical paths around the sun. To say, therefore, Newton's theory is correct and therefore it'll hold for all times is a fallacy of affirming the consequent. It's a logical error. But physics does not depend on the logical point in the sense of physics does not say I'm going to affirm the consequent, and therefore Newton's theory would hold for all time if you make these observations on the way planets move. And in fact, if it did, it would have been very embarrassed when general relativity came around, because that's a different theory than Newton's. Newton's is an approximation. So to claim that black holes exist doesn't mean that we've gone out there somehow and seen them, but there are indirect effects, and there are loads of indirect effects in physics. And one argues from the theory predicts such and such based on things that we can see, and the things that we can see should exhibit certain characteristics if we're right about our theory. And if we see those things, like in Brownian motion, then we have a validation of our theory. We don't claim that the theory is, it holds for all time. So from what I've seen in terms of the claim of black holes and the indirect evidence, including gravitational lensing, that is, if light comes from a star and gets bent, so to speak, by space-time, and you can see two images, then that's also indirect confirmation of a black hole. You can't see a black hole, of course, because it's black. Light can't escape from it. So I would disagree that there aren't any black holes. I think that there's pretty good evidence for black holes, but I don't think that there's a singularity in the sense, that there's an infinity. The Schwarzschild radius just requires that there's a certain amount of matter within this region of space. And once that happens, then you have what we would call a black hole.
Yeah. May I comment the black hole thing, because that is one of the differences which come between general relativity and dynamic universe. Black hole is the solution of black hole celestial mechanics is based on Schwarzschild's solution of a single mass center. And when we look the behavior of Schwarzschild's solution regarding the orbital velocity and an escape velocity when we close to the critical radius of black hole, it happens that when we are at a distance of 3 times Schwarzschild critical radius, then the orbital velocity exceeds the escape velocity, which means that there is no possibility for any stable orbitals to exist there. In fact, I showed in my presentation a slide which indicated that there has been detected by Planck Institute more than 10 years ago fast periods around Sagittarius A, which is the big black hole in the center of our Milky Way. And it's beyond the period limit of a Schwarzschild solution. But in the dynamic universe, we can numerically get the prediction for, it was question of periods of about 16 or 17 minutes. And in a dynamic universe, the celestial mechanics is stable down to the critical radius, and it shows that there is a minimum of the period at 2 times critical radius of dynamic universe, which is half of the critical radius of Schwarzschild black hole, and there is the minimum, which in the case of Sagittarius A is about 15 minutes. So it's very close to the observations made by Planck Institute. But the very important principal thing is that it also shows that below that 2 times critical radius, there are slow orbits which are able to maintain the mass of the black hole. So there is not question of some point mass or singularity, but it gives a very nice solution for orbits close to the critical radius that clearly can maintain the mass of the black hole. And I still analyzed where comes the problem in the Schwarzschild celestial mechanics, and it comes from equivalence principle, because according to equivalence principle, velocity obtained in free fall increases the relativistic mass in the same way as it does in the case that we are accelerating a mass object in an accelerator. But according to the dynamic universe, in order to conserve the total energy, the kinetic energy in free fall is and the velocity of momentum of free fall is obtained against reduction of the local rest energy, which is the fourth dimension momentum. And when we continue with this, we get very nice celestial mechanics, and in a sense, after that there's no let's say strange celestial mechanics in the vicinity of black hole. Another interesting thing is because the local velocity of light is equal to the local velocity of space in the fourth dimension. As soon as the space has tilted 45 degrees, it means that the free fall, the velocity of free fall becomes equal to the local velocity of light, which must be very favorable location for electromagnetic radiation build-up of electromagnetic radiation. So that I haven't analyzed that in more detail. It needs far much more. But the environment for that is very, very favorable. And that happens when we are at distance 3.4 times the critical radius. There where the tilting angle is 45 degrees. And by the way, it's the typical mass of neutron stars is about 1.5 times the solar mass, and the size of visual size of neutron stars corresponds roughly or quite precisely to the 3 times of the diacritical radius, so that we probably see the optical effect at the point where the free fall obtains the local velocity of light. It's very straightforward solution, so that there's nothing very special.
I can't comment because I haven't looked at it.
I think it's very difficult to describe here. In fact, I had some slides on that, but I hadn't time.
I think it is true that the black hole orbits will provide a critical test for your theory of dynamic universe. In the particular case of Sagittarius, I have the following comment. It is true that there are orbits which exceed, come within this critical radius, last stable orbit. But if the central black hole is rotating, if it has a spin, then it is allowed to have orbits within that critical radius, depending on the direction of the That's only comment I want to make.
Okay, but that was simply, I told the result, which is a mathematical result, so that we can...
Whether I need to respond?
No, please, no. I don't think this is useful for the audience.
Okay, thank you, Tuomo. We have had a lot detailed or more general questions, and mainly in physical problems. There is unification in physics and philosophy, and we are not keeping so large discussion about philosophy anymore because time is short. But I would like to ask from our Swedish visitor, who are specialist in metaphysics and ontology, how you see the success of today to bring together ontological discussion to natural science discussion in today. Have you any comments for in general?
Well, I'm mainly just happy to have had the opportunity to come here and in a way start. I mean, I think actually that these kinds of events where physicists and philosophers come together are fairly rare. Okay, and now maybe it was unfortunate for them that I'm not one of these philosophers who actually know the physics. Okay, I mean, I have kind of amateurish knowledge of classical physics and so on. But I have an understanding of kind of the philosophy of time, causation and stuff. So I'm hoping to in a way incorporate stuff that I learned here into my discussion with all other philosophers about those matters. But maybe that I think I can see that there are actually greater agreement about certain basic ideas about what constitutes in a way good type of reasoning and thinking about all these things. Even those that are then suggesting novel theories that are quite dramatically new, well aware of the fact that they need to support everything with empirical observations and so on. The discussion turns a lot on basically just the correct interpretation and of the phenomena. So, and I'm seeing kind of the same enthusiasm as in philosophy for falsification, started of course with an optimism about verification. So at least it gives me hope that this is a very fruitful way of proceeding, but I would say also that we're kind of in the beginning of it, at least this group here. Yeah.
Okay.
Yeah.
Thank you. And maybe Tarja, could you add something about these problems? This is some kind of meta-unification questions to bring philosophy and physics together. Microphone.
Yeah, you mean, is there some kind, is it possible to bring philosophy and physics together?
Do we have some progress in that now?
Well, I hope we can finally have more progress in that direction, because I think this kind of discussion, it is very important, and I think in the Society of Natural Philosophy we have been trying to generate that kind of discussion for many years, but it has proved to be very difficult. And for my point of view, the reason is that physicists, unfortunately, they are not very eager to discuss philosophical questions. And
it's not true.
Well, it is
Don't
my...
talk fast, don't talk fast.
Yes, it is just my opinion, and I hope I am wrong in that. So
Is Kari Enqvist reluctant to talk about philosophy?
it may be that there are just some individuals, and of course I can't generalize, and I hope that, but I hope that more, of course you are here, so you are eager to discuss, so I can't blame
Yes,
for
but
that.
the physics has to be correct. If
Yeah.
we discuss physics, the physics has to be correct. Philosophy is a different matter.
Well, yeah.
We can discuss.
Yes, but of course, if we are going to discuss fundamental questions, then we are allowed to bring up issues which may be controversial from
Yes, but they have
physicist
to be
point of view.
correct. Then.
Well,
Physics
but yeah,
is either correct or it's not.
yes, but that is
If
one.
It's not physics.
Yeah, but I have not noticed, because I have been following this DU case for 20 years, and when I first heard about it, I was thinking that very soon critical it will be studied thoroughly and found out if there is something wrong with it, because it somehow sounds too good to be true, but I was waiting for physicists to say what's the wrong point, where is the error. But unfortunately, I have not heard any, because my view is that they have actually not studied DU university theory.
So there are many of these type of theories. I mean, I've seen so many of them, and I think it's a more interesting discussion to focus more on the philosophy than one particular theory. Right? There are many variations of these type of theories, and a lot of people who claim that they have the ultimate theory and this and that. But that's not how physics evolves.
Yeah, I can understand that physicists, they have a lot to do, and there are these kind of theories which are not so consistent, or they just take one issue. But nevertheless, you know the background of Tuomo and what he has achieved, so it is not very reasonable to think that he comes up with very light theory. And I think that would be worth studying in more details.
Thank you, Tarja and Tapio, by saying that we are not alone here, so others think similarly.
Sir, may I respond to your comment? First, you are belong, because we all doctors of philosophy. Yeah, I'm a doctor of philosophy. So talking about philosophy is our job. And there's no, it's not an issue to put the physicist and philosopher together. If you want to be a good physicist, you got to be a good philosopher. Otherwise, you can be a postdoc at most. So that's my point of view. Now, unfortunately, because the theoretical physics are facing a lot of problems, if I may say, inconsistencies, and all these are closely related to philosophy. Failing to respond to the questions, many theorists are tired of philosophers. The famous complaints that shut up and calculate. Okay. That's the attitude, yeah, which I don't think is correct. we need to think about this. For philosophers, non-physicists and philosophers, what we need to do is to study the physics theory, get into it, and see what the real problems are. For physicists, our job is try to think about everything philosophically, not just playing with the math. Mathematics is just a tool. For instance, I mentioned one of the issues. I'm telling my students all the time, if you watch a leaf falling from the tree, you have a high-speed record of the picture and know the position of the leaf at each, say, nanosecond. Can you trace back to tell me where that leaf is falling from, which branch is falling from, and where it's going to land on the ground? They say it's impossible. Now look at how long have we studied the universe or the physical world? They say at most 5,000 years, right? But how long has the world been there? Much longer than 5,000 years. Then how accurate can we predict exactly what's happening 13 billion years ago with accuracy down to 10 raised to 43 seconds? And how accurate could we predict what's going to happen 13 billion years down the road? Will there be a big crunch? Yeah, all these are philosophical issues, and that actually will place our credibility to the theories. So I think physics and philosophy are together.
Okay, thank you for the third opinion.
Here I agree with you for a change.
Thank you. I'll talk to you after.
Okay, there are still many opinions around this meta question, and now we go back to normal questioning or commenting. You have some comment.
Okay, at least my opinion is so that if I want to criticize some theory, I have to deeply study and know what I'm talking about. And we have discussed about black holes, and I have studied some and go to look at the history of Einstein. 1913, Einstein and with young Grossman, they scrutinized tensor algebra, and Einstein wanted to make the gravitational field energy part of his theory, so that he sees it has contribution for the gravity. But they dropped out at last because Einstein see its minor effects on, for example, the issue of mercurio-perihelion problem. And so the next phase was so that they give us the Einstein equation or equations, and there is a problem of covariant form, and this dropping out of the gravitational field energy, it helped to take the covariant form, and so the issue is so that if we have a great gravitational field, for example in black holes, there could be some developing needs for the Einstein's theory. I have make some co-works with some Russians, And we found maybe there is a solution so that the objects go smaller and smaller near black hole, and maybe there is no event horizon. But we will study more.
First, let me clarify the two concepts. One is something that's black and very, very heavy. That's classic concept. That's not relativistic black hole. To establish a black hole, you got to establish two characteristic features. Number one, it diverges, the metric diverges on the horizon, or we call it the event horizon, at the radius of Schwarzschild radius. Number two, space and time interchanges inside the black hole. No one could establish this. If you cannot establish this, it's not an Einsteinian black hole. You can consider it as a classical heavy mass, dark mass, which I have no reason to reject its existence. What I challenge is that anyone establish those two characteristics. That is, the metric tensor diverges on the event horizon, and inside the black hole surface, space and time exchanges. So conclusion is, not all that glitters are gold. Not all that doesn't are black holes.
I have one comment to the theory. So I have tried to be devil's advocate and brought on the table the phenomena what have not studied and test what those theories, how they can describe and explain those phenomena. But I think dynamic universe, I have failed what I have brought on the table, so that dynamic universe explain those.
Well, the expansion is wrong. I mean, just the expansion explanation.
Yeah, but let's start from observations.
No, let's not discuss details here.
Okay.
It's not good for the audience.
Later.
I'm just saying, this new experiment proves that this calculation is wrong.
Send the paper to me.
Okay, thank you. It was good, Heikki, that you opened your wisdom, but I would like to ask a little bit about the bioastronomy. You spoke about the living zone. Earth and Mars have been on good places in our solar system. And what is your general opinion about the large enterprises of search of extraterrestrial life or intelligence? Have you any comment?
Yeah, I don't have any comment on this. This doesn't belong to physics.
I didn't get the question. What comments on what in particular? I'm sorry, I missed it.
Extraterrestrial intelligence.
Extraterrestrial?
Do we have any here?
Right.
Well, okay.
The only comment I have is, as far as I know, there isn't any evidence for it. Although it depends on who you talk to when you get into that area. Yeah.
That's why I asked opinion.
Yeah.
It's inevitable, okay, in the universe. It's probably inevitable.
You're right. If I may have one more question, then that would be, of course, towards the philosophers of the panel, actually. I was expecting, given the title, the concept of unification, at least in a ontological or even a more general metaphysical, whatever context you want to put it, I would expect somewhere there to see the concept of emergence. Because in physics, and I guess even in many other scientific disciplines, emergence is quite fundamental concept. I would like actually to give you now the chance if there is any connection or that we can draw when we talk about the virtues of unification or these ontologies, these entities that actually we deal within the physics or within the metaphysics, that has to do with emergence in modern physics, from your perspective, of course.
Well, emergence is not my particular area, but I can tell you what I know of others who are focusing on it. And in fact, emergence is a fairly big area in philosophy now. Something called, for instance, the Durham Emergence Project. It's been active for 5-6 years now, I think. And in many ways, what they are trying to do, I mean, usually emergence have been interesting in the philosophy of mind, because the hope has been to explain the emergence of mind in physical systems, yeah? I think the hope has been that emergence might not be so mysterious within the physical realm, right? And maybe, in fact, just two entangled particles are in a way then, since they are something more than the parts, yeah, you have an emergent phenomena, but there's no mystery.
No mystery.
No, so emergence in that sense, when you keep within the physical realm, there's no mystery. You just have something that adds up to more when it's united. So basically, and that's, in one sense, that is the classical definition of a unity. It's of a combination of parts where there's a significant connection, and that will automatically mean that it's more than an aggregate, which is just a collection of unconnected items. So basically, and that's emergence in a way. So the unity will have properties that the aggregate doesn't have. But so far, and the idea has been that if we get clearer about emergence in the physical realm, we get some idea of how that might also work for the mental. But I wouldn't want to say anything about whether that has succeeded. I mean, I was a part of a project called the New Ontology of the Mental Causation Debate for a while. But other members of the group were kind of focusing on the application to the mental, and I was on the more physical side, yeah. So I wouldn't say that it has been successful yet to apply ideas about the emergence from the physical realm to the mental realm. But the project continues, right?
So if I can follow up, so in a sense the unification is more like a synthetic process rather than a potential emergence between the constituents, right? Or can it be used like this? Or maybe not, I mean, that's the question actually.
I mean, if we manage to get the model that would explain how the mind could emerge from the physical, then we have unified, in a way, yeah, the mind and the mental and the physical. And I think the driving force of people who are working in that direction, they are operating under the idea of unification, that ultimately we should be able to understand how the mind relates to the mental, to the physical, yeah. I mean, there are many different ways to do it, even those that would assume a duality, but explain in terms of an interaction, they would be unifying. Okay, so it's not that emergence is essential for unification, and here I would at least understand unification more as a methodological approach or attitude even, so as I said, I don't think anyone here has in a way suggested that there is just this one theory ultimately that will explain everything, but rather that we get a network of theories that somehow might not fundamentally conflict, that are explaining different aspects of reality. And that would be unification. Yeah. Right? Yeah. Does that answer the question, yeah?
Yeah, I mean, even in real particle physics, this talk about the grand unified theory is a bit delusional. I mean, it's the reasons why, if there's something like a string theory from which everything in principle follows, then one can easily argue that nothing can be computed from that theory. So you need to have these theories at different levels, and there's this concept of coarse graining, which some people confuse with emergence. Some philosophers, not him, but some, where you just you end up with these effective theories like we've been discussing, and that's how physics works. So it makes no sense for me to try to describe the water in this glass from quarks, right? But I would use hydrodynamics, which is an effective theory, which in principle I can derive from these microscopic theories, but it would be totally senseless to try to calculate this from quark theory, which in principle, theoretically, I can do, but I can never in practice do that.
Thank you. Now it is maybe time to self-organize us in the universe and think, do we stop water before, academic water before, or continue to 7 o'clock? Is there any questions in the auditorium? We have had so many, so maybe some more, or in the panel. If not, I thank for my part speakers and everybody in the auditorium and participants and organizers, and give the microphone to Chairman Avril Styrman, who will soon close the session. Thank you, Avril.
Thank you. So it has been an extraordinarily illuminating experience having all you here. And it's very nice. I appreciate very much that you all could come. Hope you all had a good time. Very thankful for the audience. That very nice that you came. And hope you had some answers, questions. Hope something was clarified. Clearly, there's much disagreement about very fundamental stuff. There's some agreement too. Like everybody agrees that we should not have contradictions. All speakers agree that there's mind-independent reality. Everybody agrees that we don't want parameters for theories. Everybody agrees that we need accurate theories and we want to understand nature. But then everybody disagrees about details. So, what comes next? Who knows? But it's good to continue here. So thank you very much, everybody. Welcome the next time.
Thank you, Avril.
Thank you.